Hey, my dear NEET English warriors. Welcome to the Vedantu NEET English channel, and this is your Captain Shreyas. Before we proceed, a very important announcement. Please join the Telegram channel of the NEET English, the official channel. Link is there in the description box because you're going to get the PDF of today's session. You're going to get some special quizzes, physics, chemistry, biology separate, and also special things like the weekly free mock test from our side on Sunday. All the links will be shared only on the Telegram channel, so make sure you are a part of it. Alright, so let's begin with the chapter of ray optics, and this is going to be a long marathon. So have you come prepared mentally and physically? That's the first question. Have you come prepared? Vijay Kumar, thank you for trending. WP. Hello Sharath, hello Rishika, Teju, Krishna, nice to see all of you. Rutuja, good evening. I'm very good, thank you so much. Hello Shalini, hello Subhashni, hello Mission MBPS, nice to see your name containing Mission MBPS. Pandu is also here, maybe Champa is going to come very soon. So in this particular lecture, we are going to see questions which are based out of NCERT type, and also PYQs are also included. So it's a combination session, but mainly I'll be teaching you things so that you understand the concepts. So today's lecture being very long, so that's the reason why we will have, probably a decent amount of questions, but you'll also see equal amount of theory weightage given, so that even if you're starting from the scratch, you can understand things. Okay, so my name is Shreyas, you can call me Capto or Captain, and I have been teaching for more than a decade now, producing awesome results for all of you, and here we are today so that we can produce yet another amazing result even in 2024. Okay, so the last lecture of 2023 season of physics is right over here. Hopefully you're watching it live. Cool, the feeling of live only is very different. Awesome. Let's begin with the session, my dear students. Let's begin with the lecture. Now let's start with the concept of images and objects. Yes, Sarath, the chapter is difficult, or rather it is lengthy, so you need patience, number one. But I will teach you in a way which will make it look very simple. Don't worry about it. Happy evening, Krishna. Nice to see all of you. Film, Moji. Sir, is this the only chapter which doesn't require other chapter link? Yes. Little bit of kinematics or basic math is required, but that's basic, very minimal. Now, you must have looked at yourself in the mirror. You must have looked at a small teeny thing using a magnifying glass, or you must have used a microscope in your lab, or you might have seen using a binoculars a distant building or a mountain, or you might have seen the moon using a telescope, or you might have seen in a parking lot there is a beautiful mirror. So all these are practical applications of this particular chapter. Now, whenever you see something, that something is that object, and how it is perceived is the image, right? So say for example, right over here, this is your beautiful Champa, and Pandu is using a magnifying glass to see her. Maybe because Pandu is using a magnifying glass to see her, maybe Champa looks like this, very huge. So Champa becomes huge. So this becomes your image, this becomes your object, this becomes your object, this is your optical instrument, this is your optical device or optical instrument, and at the same time we should also show the observer. The observer generally is shown like this. This is your observer, correct? Now, when I say I see an image, means what? What exactly is happening? Let's understand that, because that will be useful for ray diagrams and other such things, virtual image, real image, and all those things. See, for example, I am telling you that I am able to see a point on the paper. I take a pen, I mark a point on the paper, meaning that if this is that particular point, the rays which come from that particular point, when they enter the human eye, remember human eye is also the lens, they are precisely meeting on the retina. They are precisely meeting where? On the retina. This is your eye lens. They are meeting on the basically retina of the eye. Then you will see that yes, there is the object which is visible here, and I can see a very detailed or a crisp or a clear image of that particular thing which is being kept in front. Now remember, the eye doesn't know where the rays are coming from. The eye doesn't care, or it doesn't even know where the rays are actually coming from. Maybe they are actually coming from a real object. Maybe there is a point, maybe there is a dot, maybe there is an ant, maybe there is a small particle. The rays are coming and they are getting converged on the retina of the eye. Does the eye know where it is coming from? No. Does the eye care where it is coming from? No. What the eye will think? It will think, oh, the rays are coming from there. That means there is something over here. There is something over here. But it is very likely actually the rays are not coming from here. Maybe it is just being perceived as if it is coming from there. Maybe it is just perceived as if it is coming from there. Just imagine something like this. Just imagine something like this. Maybe there was some kind of a device. Maybe there is some kind of a optical device over here. Okay, it could be a lens, it could be a mirror, doesn't matter. There is some kind of an optical device and the rays are coming like this. Maybe the actual object, is right over here, but when the rays go through the optical device, they might bend. So if you actually end up elongating those rays, they might meet over here. So even if your actual object is here, but because the rays bend, and when they extend backwards, they might meet over here. You might feel as if there is something over here, which is then called as the image. So these rays which are entering your eye, if you extend them till they meet, you will feel as if the rays are coming from here, not from here. So you won't see this, you will see this. What you see is the image. Is this point very, very clear? Is this concept very, very clear, my dear warriors? This is very, very important. Okay, so if you have an object, the rays might go in a very different manner. There could be some kind of an optical device because of which the rays bend. So if you extend them backwards, they meet at a point. That is where your eyes will perceive the image to be. Whatever happens before that doesn't matter. Is that clear? Okay. So there are two kinds of images also. There are two kinds of images which you can usually get. One kind of image is where you will have to extend the rays, to see where it is originating from. You will have to extend the rays and see where the rays meet. When such a thing happens before entering your eye, this kind of an image is called as a virtual image. This is called as a virtual image when you have to extend the rays so that they meet. The best example is when you see yourself in the mirror. When you see yourself in the mirror, think about it. The rays are not actually coming from the thing behind. It feels as if it is coming from behind. Behind the mirror, there is nothing. Even if you go behind and see, there will be nothing, but it feels as if it is coming from behind. That means you had to extend the rays. So if the mirror is here, you have to extend the rays to see where it is meeting. It feels it is coming from there. So that is a virtual image. Is that right? And on the other hand, sometimes it so happens that the rays actually end up crossing each other. They end up crossing each other and they actually meet. You don't have to extend it, but they actually end up meeting. They are actually meeting. So that point where they meet, what you get is nothing but called as the real image. It is called as the real image. And in order to see that real image, what one generally does is they put up a screen. They put up a screen over there, and exactly at that point you will see that, you know, that color or the dot or that particle or the image on that particular screen. So you will see that it can be obtained on the screen as well. It can be obtained on the screen as well. And the best example of a real image is your projector film or a movie theater. Projector film or a movie theater. How many of you have sat inside a slideshow or some movie theater or some kind of, you know, some 4D movie in some, you know, park or maybe some amusement park or something like that, or maybe just in your classroom you were attending some boring presentation or slideshow? How many of you have been doing that? Yeah, so that is nothing but the application or the example of real image, where you will see that the rays from the projector, they will actually meet somewhere, and where they meet is the screen. And that part on the screen where those rays meet, they get illuminated and you are able to see them. You are able to see them. Is that clear, my dear students? Very good. Everybody has sat in a projector environment. Very good. Awesome. Awesome. Now, if there are real image and virtual image, there is something called as real object and virtual object also. So when you talk about a real object, who is a real object? Anything around you is a real object. Anything around you is a real object where the rays actually originate. They actually originate from that point. Like for example, this mouse, or let's say my phone. I know that the rays are actually originating from this particular phone, and this object is right over here. This is a real object. The light from my studio is falling onto it, and I can see the rays are coming from that phone. So it is a real object. But what is the meaning of virtual object? What is the meaning of virtual object? The meaning of a virtual object is the rays are not actually coming from there. You will have to extend it so that it feels as if it is coming from there. When my phone is here, I know that the rays are actually coming from the phone. But just imagine I feel that there is a phone. I touch it and I find that there is no phone only over there. Then I will be confused. Oh my God, I can see this. But when I touch it, then there is nothing. You might have seen such scenes in some movies, in some sci-fi movies or some fantasy movies or some crazy movies where the hero tries to touch something, but actually there is nothing. It vanishes. Alright, nothing is there. It's empty. It feels as if the rays are coming from there. Then it will be a virtual object. Pandu, is it real or virtual? That's a good question. That's a good question. So when we talk about virtual object, the rays feel like they are coming from a point, but that also means that you will have to extend it. When you extend it, then you feel that it is coming from here. So that is a virtual object. That is your virtual object. Is this point very, very clear, my dear warriors? Is this point very, very clear, my dear warriors? Okay. Now, can you give me examples of real and virtual objects? Can you give me examples of real and virtual objects? Come on. Real object, almost everything around you. Almost everything around you, everything around you is real. Right? It is real, right? You can touch. Oh, this chair is there. Oh, this mat is there. Oh, this wall is there. Oh, this fan is there. You can touch and you can see that yes, it is there. Virtual. Have you heard about virtual goggles? Virtual reality goggles? Virtual reality goggles. How many of you have used that VR goggles? Some big headset comes, people wear that. And when you wear it, you feel that, okay, there is a world around you. And you can start walking. You feel like as if you are in a new world. That is virtual reality goggles. How many of you have seen people wearing it? Yeah. And you feel like as if you are in the roller coaster, as if you are on the building, as if you are in the ocean, as if you are flying. But when you touch things, nothing is there. That is virtual. So virtual goggles, virtual reality goggles, virtual reality goggles, right? I'm pretty sure you would have used that. That is a virtual object. Just giving you examples which you can relate to. How many of you have used that? Raise your hand. Already some people are saying Vijay, Bikron, Shaheen, Rutuja, Sri. Yes, virtual shows, Sara, correct. Okay. But those, virtual goggles are very, very amazing. I mean, you should definitely try that experience in case you haven't. You feel like, you're actually going to fall, you're going to, jump, so many things. So that is real virtual. The next important concept which we'll be needing in today's lecture is if there is some kind of optical device, it could be a mirror, it could be a lens, it could be a combination of lens and mirror, doesn't matter. And I find that I place the object here, the rays go like this and maybe they meet over here. The rays go over here and meet over here. I draw another ray and I see that that also meets over here. I don't have to draw more rays to find where the image is. If I know two rays are going to meet over here, it's enough for me. I know 100% if I show other rays also, they are going to meet exactly at the same point. So the point is that minimum of two rays are needed to form any image, to form any kind of image. You need just two rays. If there are more rays, it's just like double confirmation, triple confirmation, four confirmation, but it's just going to be at the exact same point. Correct. Another important thing is you have any optical device. Again, doesn't matter. You have any optical device and let's say you have an object, the rays from the object go like this and maybe they form an image over here. If now somebody takes this object and places it here, the ray will go exactly the same way and retrace the same path. It will retrace the same path and you will see that an image will be formed over here. This principle is called as the reversibility principle of light. If you reverse the direction arrow marks, you will see it will go exactly the same path that it had entered. So this is called as nothing but your reversibility of light, reversibility principle of light, where the object can be made as the image and the image becomes the object. Is that right, everyone? Very good. Yes. Okay, Sobi, definitely I will create a separate session for usage of calculus in physics after some decent amount of chapters are done, so that you at least get to know the physics part of it. Then we'll go also to the mathematical part of some chapters. Definitely, I will definitely have it. Next important concept that you must know is that if you have multiple optical devices, this is your optical device, let's say 1, then you have optical device, let's say 2, and so on and so forth. Okay, it could be lens, mirror, or combination of that. It could be anything, optical device number n, right? So then imagine if the ray from this particular object, this is your object 1, object for this lens or mirror, forms maybe an image right over here, forms an image right over here. Then what happens is, for the next event or for the next optical device, this image becomes the object. The ray will continue. Maybe the image is formed, I don't know, I'm just saying it is going to go like this, or maybe it is just going to go like this. Who knows? I'm just drawing a random ray diagram. Okay, I'm just drawing a random ray diagram. That's it. Maybe the image forms over here. This is I2. So the image of the first becomes the object for the next. So the image of this guy will become the object for the next one. It will become the object for the next one. So this will become O3, and so on and so forth. Understand that. So the point is that, you will have these kind of problems where there are multiple things happening, and you will always see that the image of an optical device will be nothing but the object for the next optical device, all right? So this happens for multiple reflections, refractions, or a combination of those. Keep these things in mind. How many of you knew all these concepts? Honestly tell me. I think I have gone right from the basics, be it virtual image, real image, be it virtual object, real object, be it how many rays you need, be it reversibility of light, and also this concept of image of this is the object of the next. These are some of the very important concepts before we proceed ahead. So now let's go to the main part, and that is where we are going to start off with reflection and plane mirrors. Although in the syllabus, if you see, reflection of plane mirrors is not mentioned, I will just be doing it very briefly just in case a question comes, because the reflection of curved mirrors is there. Plane mirror questions are little rare, but if they come, you should know it. So as a safety net, as a safety measure, we will be doing it, okay? Because if they give a question, you cannot claim as bonus, because they have mentioned reflection and curved mirrors in the NEET syllabus. So as a safety net, we will do it. Oh, no problem, Janice. You are in 11th and you are already attending 12th standard classes. Proud of you, my dear warrior. Proud of you. So starting off with reflection and the laws, very, very straightforward. If you take any surface which is reflecting in nature, then generally you show this kind of design. This design which you show is basically the silvered side, is basically your silvered side. So this is behind usually. This is usually the behind of the mirror. Whatever reflections happen in the front. So if there is a ray which falls onto it, then it is your incident ray. It might get reflected like this. Maybe some other ray might be falling somewhere here and it might be reflecting like this. So this is your incident, this is your reflected. You can see that no matter what shape or size this is, there will be a certain rules which will be obeyed, and for that what you do is you draw a perpendicular to the surface. You draw a perpendicular to the surface, which is also called as the normal. You draw a perpendicular to the surface, which is also called as the normal. And what you will see interestingly is whatever is this angle, which I call as the angle of incidence, and whatever is this angle, which is angle measured by the reflected with the normal, the reflected angle, both of them will be always equal. So this is one of the important law of reflection. law of reflection. Not just that, one more thing holds true. One more thing holds true. The incident, normal, and the reflected. If you draw these three rays and you show a plane which contains them, all of them will be in the same plane. The incident, the reflected, and the normal are always in the same plane, are always in the same plane. So that completes your law of reflection. The two laws are incident angle and the reflected angle are always same, and all the three, incident, reflected, and the normal, are going to be in the same plane. Is that clear, my dear warriors? Perfecto? Very good. So, is this only true for plane mirrors or is it also true for curved mirrors? Simple question. Is it true for plane mirrors only or is it true for both plane as well as any kind of curved mirrors? What do you think? Come on, put it up in the chat box. I'm waiting to hear your answer. Yes, very good, my dear students. Some of you probably got confused. Yes, it is. It is for both. It is for both plane as well as curved mirrors. There is no such restriction that you should only use in the case of plane mirrors. No. Look at this. This is a curved mirror. Any kind of surface will follow, these laws. Each small part is like a small plane mirror. Small plane mirror. Very good. So now, for example, I give you a scenario where there is a part of it and I call this as my mirror. So this is my mirror for now, and I show a normal to it. I show a normal to it. I show a normal to it. And then I show the incident ray. I show the incident ray which is coming like this. Let's say the mirror was not there, then the ray would have traveled like this. Then the ray would have traveled like this. But because the mirror was there, the ray went over here. So, do you notice this is the angle by which it has deviated? So, this is also called as the angle of deviation. Angle of deviation. The ray was supposed to travel like this, but because there was something in between, it got deviated over here. So that is your angle of deviation. Is that clear? Everybody with me? Very good. So how much will this be? Well, that is not that difficult to find. This is I, this is R, this is R. I, R and this delta together will make 180 degrees. You can see it is 180 degrees. So delta, won't it be 180 minus I minus R? But wait a minute, I is equal to R. So this will be 180 minus I minus I. So won't it be 180 minus 2I? So that is the angle of deviation. That is the angle of deviation by a simple mirror. There was a question which has come previously also and in many different ways, maybe even in your boards it might come. A ray of light makes 30 degrees with the mirror. So then find the angle of deviation. A ray of light makes 30 degrees with the mirror. Question is, find the angle by which the ray gets deviated. Let's see how many of you give the correct answer in the chat box right away, right now. So if you start drawing the diagram, you will quickly realize what is the catch in the problem. How many of you are saying 120? Let me see. Are you saying 120? Sure. Pakka? See, some of you gave different answers now. If this is how the ray is entering and getting reflected, this 30 degrees with the mirror. So this is 30 degree. So this is going to be 60 degree, which is going to be your angle of incidence. So angle of incidence is not 30, but it is 60. It is always measured with the normal. So your angle of deviation is 180 minus 2 into 60. 2 into 60, 120. 180 minus 120 is just going to be 60 degrees. Perfect. So delta is 60, not 120. Wow, we have some smart bunch of students who are marking 60 degree. Very good, Krishna, Sanvi, Rutuja, Anugna, Abhinya. Awesome. Yes, that's the correct answer. There was one more question which came, and let's see if you guys can answer this. There were two mirrors and they were inclined at an angle. There were two mirrors and they were basically inclined at an angle. And the angle by which they were inclined was theta. And what happened is, one ray hit the mirror 1, hit the mirror 2, and then came over here. So first time it got deviated, second time also it got deviated. So there were two deviations. So there was some total deviation over here. Question is, find the total deviation. Find the total deviation. How do we do this particular question? So over here, I don't even know what is the angle of incidence. Okay, let's start by assuming certain values. So let's say I drop a perpendicular here. Let's say I drop a perpendicular here. Let's say I call this angle. Let's say I call this angle as I1. So even this angle will be I1. Let's say I call this angle as I2. So even this angle will be I2. Correct? Okay. So now if I have to write down what is the total deviation, the total deviation will be deviation in the first case plus the deviation in the second case. I was going here. First time I deviated by 10 degrees. Next time I deviated by 30 degrees. First time I deviated by 10 degrees. Next time by 30 degrees. So total will be 10 plus 30. So 40. So same way over here. First time I deviated by delta 1 degrees. Next time I deviated by delta 2 degrees. So total deviation will be delta 1 plus delta 2. Agree, disagree? Perfecto? Very nice. Now what do we do? Acha, delta 1 is 180 minus 2i1. Delta 2, 180 minus 2i2. I know you guys are thinking, sir, what to do about that I1, I2. Don't worry. 180 plus 180, 360. 2 is common. What is remaining? 2 times I1, I2 in brackets. So that is your delta. But I don't think I should leave the answer like this because I1 or I2 were not given to me. So I will think now. What else can I do? Look at this particular angle. Can you tell me how much is this angle in terms of I1? I think you know it. Because you know this is 90 degree. You know this is 90 degree, and out of that this one is I1. So how much will be the remaining angle? Come on, think about it. So if this is 90, this is I1, won't this be 90 minus I1? Won't this be 90 minus I1? How many of you saw that? Very good. Similarly, my dear warriors, what do you think is this angle? This angle is 90. Out of that, this angle is I2. So how much is this angle? 90 minus I2. And do I know a property of the triangle? Do I know some property of a triangle regarding angles? Of course I know. Sum of the angles of a triangle are 180. Sum of the angles theta plus 90 minus I1 plus 90 minus I2 is going to be 180. Now see what magic happens. Theta 90 becomes 180 and I1 I2 I send it on the other side. So it will become plus I1 plus I2. 180 gets cancelled. So theta is I1 plus I2. Oh, magic happened. I1 plus I2 is theta. So I'll just replace this with theta. So I will get delta is 360 minus 2 theta. Best part, it is independent. It is independent of the incident angle. independent of the incident angle. It only is depending on this theta, which is the inclination between the two mirrors. So cool problem. How many of you loved it? Isn't it? So we have just used basic geometry. That's the reason why I did geometry and trigonometry before, because you will get that push, that momentum towards these things, right? Shall we move ahead to the next one? Shall we move ahead to the next concept? Okay. So till now we have studied the laws of reflection. Till now we have seen, what is deviation. Next, let's also think about the image formation. When you have a plane mirror like this and you take an object over here, you take an object, let's say over here, then if I show any two rays, that's enough for me to find where the image is. This ray will go here, it will get reflected like this, where this angle will be equal to this angle. I can show even this ray which falls normally, and because it falls normally, it will come back via the same path. So now I have two rays which are diverging. Look at this. This ray went like that and it is going this way, and the other ray is coming like this. So 100% they will not meet forward, but if I extend them backwards, they will meet somewhere. So this is the place where the image is formed for this particular object. This is the place where the image is formed for this particular object. But your object need not always be a point object. It could be made of many points. When an object is made of many points, what is the name given to it? What is the name given to it? Right now, this is a point object. This is a point object. This is a point object. But imagine you had an object with many points. Then for each point an image will be formed. For each point an image will be formed right over here. Something like this. For each point an image will be formed over here. Something like this. By the way, what is this object called? How many of you can put up that name? Yes, that is then called as an extended object. It is called as an extended object. So for a point object, the image is also a point image. The image is also a point image. But for an extended object, the image is also an extended image. Extended image. Very good. This is something which you should know. So how this proceeds is basically you take one point and you see how the rays are getting reflected and you see where the image is formed for that point. Then you take any other ray and see where it is getting reflected and see where the image is getting formed. Similarly, you take any other ray and you again see where the reflected ray is going and extend it behind, and that is where the image is formed. So you draw multiple rays to figure out each image of each point, and that's how you get the total image. That's how you get the total image. Very good, my dear students. So there are some important properties which you must know. So say for example, you have a Pandu and this Pandu smiles like this, and he is a right-handed bowler. He bowls with his right hand. Okay, he bowls with his right hand or bats with his right hand, doesn't matter. Some example. And this is a mirror. This is a mirror in which in front of he's standing. So you will see an image something like this of Pandu, like this, and you will see like this, like this. If he is right-handed, will he be right-handed? If this Pandu is right-handed, will this Pandu be also right-handed bowler? No, that Pandu will be left-handed bowler. Yes or no? That Pandu will be left-handed bowler. Yes or no? So the images, what are the characteristics? It is called as laterally inverted. Laterally inverted. Laterally inverted. So left becomes right, right becomes left. Left becomes right, right becomes left. Very, very commonly observed. And that is the reason why, if you would have seen an ambulance, guys, you are going to work in hospitals, you would have seen an ambulance. Come on. On that ambulance, have you seen how the words of the ambulance are written? Have you seen how the words of the ambulance are written? Can somebody type it for me? I don't think so. It is not so easy to type it on the keyboard. Yes, the words of an ambulance are written in such a way that if you see it in the mirror, then you see it properly. Because they are laterally inverted. Left, right, right, left. Yeah. So why? Because when an ambulance is coming, what should you do? Should you block the way or should you make a way? Should you block the way or should you make the way? You should make a way. And how do you make a way? When you realize that there is an ambulance coming, you will see it in your rear view mirror. So in the mirror, the words of the ambulance, when they are seen, okay, yes, I need to make way. And hopefully you will be the person in that ambulance, treating patients. Hopefully you will be the person who will be waiting on the other side in the hospital to treat the patients. Because that's where your dream is. You should feel proud about that you will be saving somebody's life. You will be treating somebody who needs some, God-like person, which is nothing but a doctor. That will be you in some years. Hai na? So I hope you got goosebumps listening to this. The next important thing is that whatever is the distance of the image is also the distance of the object. So I can say the image distance is also the object distance. That is also another thing. Also the object height is equal to the image height. Also equal to the image height. Also I can say that the image is erect. Sometimes certain instruments invert the image. Sometimes some instruments invert the image. Maybe a magnifying glass, you might have seen, sometimes inverts the image also. So image is erect means if you're standing like this, the image is also standing like this. It's not like you see the legs on the top and the head is below, right? That doesn't happen. So the image is erect, the image is laterally inverted, it's of the same size, it's at the same distance. Lastly, the image is virtual in nature. It is virtual in nature. But I put an asterisk over there. Why do you think Shreyas Sir has put asterisk over there? Is it always going to be virtual? Why is it virtual? First think about it. Because the rays feel like they are coming from here. This point image is definitely virtual because the rays feel like they are coming from there. But is it always necessarily true? Think about it. Is it always necessarily true? Because if you have the rays coming like this and I know it is getting reflected in this particular manner, so I had to extend it. So I know this is virtual. This is a real object. This is a virtual image which is formed. Is it always necessary that it is virtual? The answer is no. I'll give you a simple example. Look at this. Imagine there is some lens over here. And you place some object over here. This is basically a real object. And from the real object, the rays go like this. Correct? The rays will go like this. And what will happen? They will merge somewhere. So this is the point where the image is formed. This is the point where the image is going to be formed, correct? Where the image is going to be formed because of that lens. Everybody understands this? Everybody understands this concept till here? Okay. Now what I do? I introduce a mirror somewhere over here. I introduce a plane mirror somewhere over here. Now will the rays be able to reach here? Yes or no? Obviously not. So I have to remove these rays because they won't be able to reach here. but I will show dotted line to show that the rays wanted to meet here. The rays wanted to meet here. Now, what did I tell you about one or more than one optical instruments when they are present? Then the image of the first optical instrument becomes the object for the next optical instrument. So, if this image is formed by this lens, that image will behave like the object for the mirror. It will behave like the object for the mirror, and I know the rays can't go there, so they will have to reflect and meet over here. So this is where the final image is formed, and this image is 100% a real image, but this object is not a realistic object. I know nothing can be there behind the mirror, so this is a virtual object. This is your virtual object because the rays are not actually meeting there. Got it? Yes. Oh, we have a Baswa sir over here. How many students think physics is the most interesting subject? Oh, thank you, Baswa sir, for joining the physics class. I'm pretty sure students are finding it interesting because, you know, see, we have even our amazing teachers sitting in everybody else's class, because I also want to learn botany, I also want to learn zoology, I also want to learn chemistry. So I keep attending classes and I keep gathering information. Maybe I remember a few things, maybe I don't remember a few things, but it is fun. And also I keep seeing you guys, how you attend the classes. I also want to be the student. Yep, very good. So I hope you understood that a plane mirror can also make up a real image using a virtual object. Is that point very, very clear, my dear warriors? Is that point very, very clear, my dear warriors? That's the reason why I put a star mark over here. Why that star mark? Because it can be virtual or even real, depending on the type of the object. So for a real object, virtual image. For virtual object, real image. That's how it proceeds. Cool. Awesome. Awesome. Next important thing, by the way, this slide was very important because I had mentioned all the important characteristics of the plane mirror's image being formed. Now, the next important thing which you should know is regarding the velocity. Does it happen that you are running towards a mirror? Imagine you are running towards a mirror with, let's say, 2 meters per second. Then what speed will the image run towards you? What speed do you think the image will run towards you? Obviously, the image will also run towards you with a speed of 2 meters per second. So if the object goes like this with 2, the image also goes towards you with 2 meters per second. Correct? Very good. Let's take up another example where imagine the object moves like this with a speed of 2 meters per second. The mirror is here, and where do you think the image will go? Where do you think the image will go? Come on, my dear students. Where do you think the image will go? Where do you think the image will go? Will it go up or down? Obviously, if the object is going here, if the image goes like this, you will feel that there is a ghost. How can this happen? So 100% the image has to go with 2 meters per second like this only. Awesome. Now, what will happen if, imagine, the object is at rest, but the mirror is being moved like this with a speed of 2 meters per second. What do you think the image will do? Look at the manner in which the mirror is being moved. The mirror is being slided like this. What do you think the image will do? Will the image move at 2 or some other speed? Which direction do you think it will move? My dear students, in this particular scenario, when the mirror moves, how does it matter? The object and the image will have to stay in front of each other. It's like there is a train which is moving in front of you. You are seeing yourself in the window of the train or the bus. Even if the train moves, you will still see your reflection in front of you. You will still see your reflection in front of you, whether the mirror moves or doesn't move. So hence the image will be at rest. The image will be at rest Even here, I would say the image is going to be at rest. Is that clear, my dear students? Yes, 0. Very good. Abdul, Vijay, Anugna, Rutuja, Krishna. Awesome. So we have real people, not ghosts. Next, what if the object is at rest, but just like over here, horizontally? So I make this mirror move this way with a speed of 2 meters per second. Then what do you do? Then what do you do? Come on, my dear students. Come on, my dear students. What do you do? Yep, think carefully. Now, I don't think the image will move at 2 meters per second. The mirror itself is moving away at 2. So, with respect to the mirror, the image is going at 2. With respect to the mirror, the image is going at 2. So, if I am the mirror, for me the image is going at 2 because I am going with 2 speed with respect to the object. So, if this is the object, I am going with the speed of 2 meters per second. So, for the mirror, the image is going at 2 meters per second. But I myself, I am moving. So, with respect to the ground frame, it is going at double the speed. It is going at double the speed. It will go at 4 meters per second. 4 meters per second. Now, you get some combination questions where mirror, etc. both are moving. So then it becomes very confusing. Instead, I will give you a simple formula. Instead, I'll give you a simple formula. So if you have a mirror and let's say it is moving with a velocity of Vm, it is moving with a velocity of Vm, and let's say you have an object and you are moving that object with a velocity of Vo, and this is the image which is moving at some new velocity Vi, which is moving at some velocity Vi. Then if you make the mirror as your frame of reference, if somebody makes the mirror as your frame of reference, then what you will see is the object's velocity with respect to the mirror. You will also see the image's velocity with respect to the mirror. For the mirror, if the object comes here, the image should also come here with the same speed. If I am the mirror, if the object comes like this, the image should also come like this with the same speed. That means they are always going to be what? Equal in magnitude but opposite in direction. Equal in magnitude but opposite in direction if you are sitting on the mirror. If you are sitting on the mirror. So I'm going to give you a very important trick, my dear warriors. So VOM is negative of VIM. This is relative velocity concept. Velocity of object with respect to mirror is LHS. Velocity of image with respect to mirror is RHS. So V12 is V1 minus V2. So this will be VO minus VM is equal to minus VI minus VM. Now you rearrange it. So it will become, do one thing, take VI on this side, take VI on this side, take VO on this side. So what will happen? First of all, minus VM will become plus VM. Then minus minus will also become plus VM. And VO is taken over here, so minus VO. So therefore, velocity of image will be 2 times velocity of the mirror minus velocity of the object. You can directly use this expression. You can directly use this expression. Helps you in many complex scenarios. Helps you in many complex scenarios where object and image both are moving. Correct. Object and mirror both are moving. Just to give an example, imagine there is a mirror going like this with a speed of 2 meters per second. And let's say this object is going with a speed of 5 meters per second. Then the question is, what is the velocity of the image? That's the question. That's the question. Let's use this. Vi is 2Vm minus Vo. Vi is nothing but 2Vm minus Vo. Now please remember, this is a vector equation just like kinematics. Remember, plus minus matters. Same thing also. You have to be careful over here. When I write velocity of the mirror, do you see it is going left side? Usually we take right hand side direction positive, left hand side direction negative. So this will be nothing but -2, and velocity of the object is nothing but just 5. So this will become -4 minus 5. That means it will become -9 meters per second. What does this mean? -9 meters per second. It means that your image is going like this with 9 meters per second speed. Image is going with 9 meters per second towards your left hand side. Is that clear, everyone? How many of you understood how to use this equation with sign properly? Everybody with me on this? Cool. Now, next important concept comes is how much part of the mirror do you often or generally need? How much part of the mirror do you generally need for seeing some object? Say for example, I'm trying to see this particular object. And let's say my eyes are right over here. This is where the observer is. This is where your observer is. This is where the object is. And I do not really know how much of the mirror do I really need. Just one second. Okay, so I've just shown some random mirror over here. I don't know how much of the mirror I'm going to exactly use to see this particular object. So what you do is try to look at the most extreme points of that object, the uppermost, lowermost, leftmost, rightmost, frontmost, backmost. So try to see the extreme points. If you can see both the extreme points, then you can see all the points in between of that object. Correct? So the extreme points are the one on the top and one at the bottom. So if I just show the rays which are probably going to come and reach the eye, so probably it will come like this and it will reflect and probably maybe go like that. Just one second. Maybe it will go like this. Maybe it will go like this over here. Correct? Then if you take the bottom point of that object, maybe it might reach over here and maybe it might again reach the eye over here like this. Now all the other rays which are coming from these points will be falling somewhere in between these two extreme ends and they will be reaching the eye. You take any point now after this on the object. You take any point now on the object. Those rays will lie in between of these two extreme lines, yellow and green. That means, is this part of the mirror needed? No. Is this part of the mirror needed? No. So can I then say that I don't need this mirror? I don't need this mirror. The only part of the mirror which I will be needing is only this much. Only this part of the mirror is used to see the image. This part depends on the object size. It also depends on where the observer is. If the observer goes far or close or shifts the position, this size might vary. If the object also changes the size or the location, this part might vary. Understand that. Is that very clear, my dear students? That's how you do these kind of questions, where you show the extreme rays. And you are figuring out how much part of the mirror is needed. You also get another kind of question where the mirror is fixed. The mirror size is fixed. And maybe you might be having some object over here. And you are interested where and all can you see the image? Which and all places can you see the image? So what you do is simply start by showing all the possible rays which can come from that object. Maybe it will come like this, like this, like this, like this. Now if you notice, the rays will go in all the possible directions, but only few of the rays will interact with the mirror. So try to see which are those rays which interact with the extreme ends of the mirror. Try to see those rays which interact with the extreme ends of the mirror. Like one of this ray, it will go like this and maybe go like this. Another ray probably go like this and probably go like that. Correct? So here we showed it like this, going like this, and going like this. Anything in between that is going to interact with the mirror. It's also going to reflect and going to come over here. Perfect. So only these rays can get reflected from the mirror, but if I show any other ray, it is not even going to interact with the mirror. It's not even going to interact with the mirror. Are you able to visualize this? Are you able to see this? They are not even going to interact with the mirror. That means if you are an observer here, will you able to see the image? Will you be able to see the image? Yes. But if you are an observer here, will that observer be able to see the image? No, because the rays won't be reaching that eye. The rays won't be reaching that eye. Same way, if you are an observer here, also it will be okay. If you are an observer here, also it will be okay. But if you are an observer here, it will not be okay. You won't be able to see the image. You won't be able to see the image. So this particular region in which you are able to perceive the image, that is called as the field of view. That is called as the field of view. Is that point very, very clear, my dear warriors? Yes. There is no need of red. Correct. These parts are also called as your blind spots. Blind spot. Have you ever faced that when you're riding a bike, scooty, whatever, in that rear view mirror, you can't see everything around you. Only a certain part behind you can be seen. That is your field of view. But a certain part, suddenly you're like, oh, where did this bike fellow come from? Where did this fellow come from? Because he was or she was in the blind spot. Understand that. Okay? So this is the concept of it. If you are in certain region only, you can see it. But if you are not in that field of view, then you will be in the blind spot region. Yeah. Even in your eyes, there is a blind spot, but the brain beautifully manages it. One more concept which you should know regarding plane mirrors is that if you take two mirrors parallel to each other, these two mirrors are parallel to each other, and let's say you are standing in between, then you will get multiple reflections happening and you will get multiple images on both sides. Has this ever happened to you, especially at a salon or a barber shop or even in a mall in the changing room where there are multiple mirrors on both sides? And then you suddenly find an army of you, replicas of you on both sides. Have you faced that or no? Have you seen that or no? You will see multiple images of you like this on both the sides. This is because of multiple reflections which are happening. So there will be how many number of images of you? So all this is because of multiple reflections. I'm not showing all of them, but just to visualize this, there are multiple reflections. So there are multiple reflections which are happening. So these are all images. But can you count the number of images? Can you count the number of images, my dear warriors? How many images will be there? The answer is there will be infinite number of images. There will be infinite number of images. Yes. But the problem is you won't be able to see all the infinite images because they will become so far away, they'll become so faint that they will not be perceived only by your eye. So mathematically, there are infinite images, but what you can see may be some 30, 50, 100, 200 maximum number of images. After that, it becomes very dim. It becomes very dim, or it becomes, very, very far away. But if by chance you put those mirrors at an angle, if you put those mirrors at an angle, something like this, and you then stand over here. Try that probably in a changing room. Try that probably in a changing room. If the door has a mirror, try to tilt that door or open or close that door. You will see now the mirrors are at an angle. You will see the images are no longer on a straight line. The images are no longer on a straight line, but that army becomes something like this. But that army of you becomes something like this. They go in a curved path. They go in a curved path. Something like this. They go in a curved path. They go in a curved path. Something like this. And you will see as if your army is having a round table conference. Your army is having a round table conference. So they are on a circle and the number of images are finite. Finite number of images, not infinite. Finite number of images in a circle. Try this out. Why should I just, tell you blindly? But try this out in a mall. Yep, in a circle. Definitely. Such a beautiful phenomena to witness. And guess what? How many images are formed? For that, you just extend these two lines and see what is theta. Just see what is theta. And then divide 360 divided by theta. See what it is. If it is odd, then the number of images is 360 divided by theta only. But if by chance, if it is even number, then the number of images formed is 360 divided by theta minus 1. Direct formula. Okay, so if it is even, then make it odd by subtracting 1. If it is odd, just leave the answer as 360 by theta only. So say for example, I tell you that listen, the mirrors are at an angle of 120 degree. The mirrors are at an angle of 120 degree. So what will be the number of images which are going to be formed? So what you do is, if you are placing the object here, divide 360 with 120. What will it be? 3, right? So hence, it is an odd number. So the number of images will be 3. The number of images will be directly 3. But say for example, the mirrors are at an angle of 90 degree. Then if I want to find the number of images because of that object, divide 360 with 90. How much will it be? 4. But 4 is an even number. So what will you do? You will subtract 1 from it. It will be 3. It will be basically 3. Is that clear? Everybody? So this is the simple way in which you can find the number of images. You just need to know the formula. Very rarely they might ask a question on this, but if they ask, you know how to do it. Shall we do some questions on plane mirrors? I've done plane mirrors in detail. I'm pretty sure very few teachers, forget English medium teachers, but very few teachers will do this in this much detail specifically for NEET. For JEE, there is more detailed plane mirror analysis for JEE Advanced specifically, but for NEET, that is not at all needed. It is not there only in the syllabus. Let's do this. It is desired to photograph the image of an object placed 3 meters from a plane mirror. The camera, which is at a distance of 4.5 meter from the mirror, should be focused for which particular distance? That's the question. Let's have a look at it. Okay. So you want to photograph the image of an object which is 3 meter from the plane mirror. So the object is here. The mirror is over here. This distance is given to be 3 meters. And where is your camera? The camera is at a distance of 4.5 meters, something like this. So this is, let's say, your camera over here. Okay, so this is given to be at a distance of 4.5 meters from the mirror itself. So the object's image will be formed right over here, and that distance will be basically 3 meters. So if the camera has to focus on the image, how far is this distance going to be? 4.5 plus 3. 4.5 plus 3, which is 7.5 of a meter. 7.5 is D for doctor, or AIMS Delhi. D for doctor. How many of you wrote D for doctor? Very good. Is that okay? So that's how this question has to be solved. This was based on the concept that object distance is equal to the image distance. So the image is formed right behind, exactly 3 meters. So when I see through the camera, then I'll be focusing on the image, which is 4.5 plus 3, which is 7.5 meters. Awesomeness. Moving on now to the next question. Two plane mirrors such that they are parallel to the each one, so that the light ray which is incident on mirror 1 is parallel to the next one, and the reflected light is parallel to the first one. The angle between the two mirrors is, okay, I'll tell you. First of all, draw a diagram. It will be very, very clear. This is mirror 1, this is mirror 2. I want to find this theta. As per the question, the light which falls on mirror 1 is parallel to mirror 2. See this? It is parallel to mirror 2. It gets reflected, and the light which is reflected back again, the light which is reflected back again, that light is parallel to mirror 1. Okay, perfect. I hope you guys got it. This ray is parallel to this ray is parallel to this ray. Question is, what is theta? Okay, I'll tell you what. Do you remember I told you what is the deviation formula when there are two mirrors? We just derived it, right? 360 minus 2 times of theta. 360 minus 2 times of theta. But I want to find theta over here. So 2 theta will be 360 minus delta. So theta will be 360 minus delta divided by 2. 360 minus delta divided by 2. Is that right? Can I find the deviation? Definitely. Pay close attention to the rays, how they are going. The ray which was going like this, it turned like that, turned like this. It turned like this, correct? And it started going like that. And then again it turned, and then it started going like this. It started going like this. So can you guess the total amount by which it has deviated? Can you guess the total amount by which it has deviated? See, it was going here. See, it was going here. It came back and it has gone like this. It has gone like this. So if you just compare this one with this one, you will realize it has not only turned by 180 degrees, but an extra additional angle. How much will that angle be? Well, if this is theta, won't this angle be also theta? If this is theta, this will be theta. Won't this angle be also theta? So how much did it turn by? 180 degrees plus theta. 180 degrees plus theta. How many of you visualize this? How many of you visualize this? Come on, my dear warriors. It turned by 180 and an extra amount. Turned by 180 and some extra amount. And that extra amount was none other than theta. So what will be the deviation? This will be 180 plus your theta. 180 plus your theta. So that's all that is there. So maybe I will better put it over here only. So this delta will be 180 plus your theta. So solve this and you'll get the answer. So 2 theta, this is minus theta. So bring it over here, plus theta will be 360 minus 180. 360 minus 180 is 180. 2 theta plus theta is 3 theta. So theta will be 60 degree. 60 degree is option B. Done, done, done. 60 degree, that's the answer. The concept was here. How many of you loved the concept? How many of you loved the manner in which I used this concept? How much did it deviate by? So a lot of people think, sir, it deviated only this much. No, don't go shortest way. See the actual way by which it has deviated. It's like I was going here, I turned and then I turned more. So I turned by 180 plus more theta. So that is my deviation. Substituting, you will get the answer. Loved the question, my dear students. Shall we go to the next question? Yep. Beautiful, right? So that's why you should attend the classes with me. And I hope you have smashed the like button. And if you have not yet joined the channel, subscribe it right away, right now. And the most important thing is you should talk about the Vedantu NEET English channel in your school, with your batchmates, with your cousins, with your juniors, anytime. You should be like the best team for NEET is right over here. And the best part is specifically for students who are studying in English medium, or maybe you do not understand Hindi channels. This is the channel for you. This is the biggest channel in the country. So you have to talk about this. The man is 180 centimeters tall, eyes are below. If he wants to see himself from toe to head, he uses a plane mirror at a distance of 1 meter from him. The minimum length of the plane mirror is how much? Yep, let's have a look. Thank you so much, Pandu. Thank you so much, Sanvi. Thank you, Krishna. Thank you, Shaheen. Let's solve this question. So here is our person. Here is his eyes. That's okay. I can just show it like that. And there is a mirror in front of him at certain distance. At certain distance. I don't think we need that distance also. If he wants to see himself, the minimum length of the mirror required is, it's clearly mentioned, this is how much? 180 centimeters. I don't even need that. Let's say I call it as H. Let's say I call it as H. Okay. And let's say this distance, let's say this distance, I call it as D. Now, the image of this person will be formed right over here. The image of this person, exactly the same height, I should show over here like this. Okay, and this image is also going to be formed at a distance D. This image height will also be H. If this person wants to see the image, that means the rays from there should reach his eyes. The rays from there must reach his eyes. The rays from there must reach his eyes. These are the two extreme rays. They have to reach his eyes. Do you see two triangles, one small and one big being formed? One small, one big being formed. And then can you also notice that the small triangle and the big triangle are actually similar triangles? They are actually similar triangles because this angle is equal. It's just zoomed in, zoomed out version. That's all. Very good. So if they are similar triangles, their sides are in the same ratio. Sides, heights, etc. are in same ratio. Can you see the height of the small triangle? The height of the small triangle is going to be D, whereas the height of the big triangle is going to be 2D. If this is D, this is 2D. If this is X, this is 2X. If this is 1, this is 2. All the sides are in the ratio of 1:2 in this case. So if this is X, this is 2X. If this is 1, this is 2. If this is 2, this is 1. If this is X, this is X by 2. If this is H, this will be nothing but H by 2. So the size of the mirror required will be only this much. The remaining part of the mirror will not be needed. So H by 2 is 90 centimeters. That's the answer. You don't even need D. Don't even need where the eyes are. That is all stupid information, waste information, useless information. Okay, don't even need that. We just use similarity. Exactly. Did you love the way I solved this question? Did you love the way I solved this question? Cool. If you loved this, then I think you will love this question as well. Look at this. This is question based on field of view. There is a point source of light B placed at a distance L in front of the center of a mirror of width D hung vertically on a wall. Okay, a man walks in front of the mirror along a parallel line to the mirror, a distance 2L from it as shown, greatest distance over which he can see the image of the light source in the mirror is. I will explain. You might be confused reading all these things, hai na? Don't worry, I am there for all of you. See, there is a light bulb over here. This light bulb will emit light rays in all the possible directions. Some light rays will go here, they will get reflected. Some light rays will go here, they will also get reflected. Some light rays will go till here, they will also get reflected. These light rays will get reflected. These light rays will also get reflected. But then there are some light rays, like you can see, they will not get reflected. Now this Pandu is walking on this line. Tuck, 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 tuck. He is walking on this line. So you can see clearly there is only a certain region. There is only a certain region which is in the field of view. Otherwise, everything else is in the blind spot. Correct? Everything else is in the blind spot. The question is, what is this distance? The greatest distance over which he can see the image. So what is this distance is the question. Are you able to visualize what the question is now? Did you understand what the question is now? Yes. Yes. Awesome. So how to solve this? I'll just redraw the diagram so that you are very, very clear about it. So this was the mirror of distance D. Then you also have a source at a distance of L. This is basically at a distance of L. This is your object, and that line is at a distance of 2L. That line along which you basically walk is at a distance of 2L. Okay, so basically this distance from here to here is 2L. That's what it is. So let me just show the extreme rays. That's enough, more than enough for me. This is one, this is one. The other one is right over here. The other one is right over here. Correct? Doesn't it look like a folded paper? You take, have you done this while making an aeroplane? You fold along this line, you fold along this line. So basically it looks something like this. Doesn't it look like a folded paper? How many of you are able to visualize that? If you are able to visualize that, then we'll go ahead. So it looks like a folded piece of paper. So why not open it? Why not open it and make it look like this? So I will call this now O prime or O1, whatever. So if this was L, how much will this be? If that was L, how much will this be? Come on, my dear students. Even this distance will be L only, right? This distance will be L only, right? Now I think you can see two triangles, one small and one big. I think you can see two triangles. One is this small little triangle and the other one is this big triangle. This big triangle. Okay. Aren't these two triangles identical, similar in nature? Aren't these two triangles similar in nature? Yes or no? Aren't these two triangles, small and the big one, similar in nature? Because it's just as if you are expanding that. That's all. It's as if you are expanding that. What are the heights of these triangles? This height is D. Sorry, not D, L. This height is basically L. From here to here is L. How much is the distance from here to here? Here to here 2L. This is L. So total height, the total height, won't it be 3L? Total height, won't it be 3L? 2L plus L. So what is the ratio? 1:3. 1:3. So if this is L, this is 3L. So naturally, my dear students, think about it. If this much part is D, how much will this much part be? this will be 3D. So from here to here, this distance is 3D, in which you will be having your field of view. Hence the answer is 3D. Hence the answer is 3D. You can see that right over here. Clear? Got it? Enjoyed it? Moving on to the next question. Find the velocity of the image when the object and the mirror both are moving towards each other with 2 and 3 speed. With 2 and 3 speed. Come on, figure this bit out. Find the velocity of the image when the object and the mirror both are moving towards each other with these speeds. So, if I take the object is moving at a speed of 2 meters per second, the image, sorry, not the image, the mirror is moving at a speed of 3 meters per second like this. I want to know what is the speed of the image. Use the formula. Velocity of the image is 2vm minus vo. Velocity of the mirror is minus 3. Velocity of the object is plus 2. So this will be minus 6 minus 2, which will make it minus 8. But the question is find the speed. So the magnitude will be just 8. So answer will be option A. Just check this out. Yes, it's A for Ames Delhi. Yes, it is A for Ames Delhi. The question was just on the speed, not on anything else. Correcto? Shall we move ahead? Everybody understood? Always use the sign convention. Vm is negative because left side. Vo is positive because it is right side. Substitute, you automatically get the answer with the correct sign. But sign was not needed over here. Next, you are in a car and going along a straight road with some speed, and there is a mirror on a truck which is going at a speed of 70. What will the speed of the image be from the ground frame? What will the speed of the image be on the ground frame? Let's understand the question again over here. So the car is basically the object which is going at a speed of 50. The mirror is attached on the truck. The mirror is attached on the truck. And the truck is going with a speed of 70. The truck is going with a speed of 70. So the question is, with what speed will the image go? Again, use the same formula. Vi is 2em minus vo. Velocity of the mirror, how much is it? Plus 70 because going towards the right side. Velocity of object, how much is it? 50. So 140 minus 50 will make it 90. Is 90 there in the answer? Yes. Option number 4, 90 kilometers per hour. Isn't this formula very, very helpful? Especially when the speeds are along the perpendicular direction of the mirror. So if the mirror is like this, the speeds are like this, then it is very simple. If the mirror and the objects are going parallel, then though it is very simple. I showed that case to you in the previous slides. Only problem happens when they are like this. Okay? So I hope these things are very, very clear. Simple formula. Great. If two mirrors are kept at 60 degrees to each other, then the number of images formed, I have given you the formula. You are not going to draw the ray diagram in the exam. You're going to save your time because you attended my class. So first thing that you will do is divide 360 by 60. The answer is 6, which is an even number. So the moment it is even number, you subtract it with 1. So I think the answer must be 5, which is Ames Delhi. Yes, Ames is the answer. All India Medical Institute of Sciences. Awesome. Best formula, right? So if you know these formulas, you will save a lot of time. Or else you will be stuck in a big loop. And in NEET exam, these kind of questions only are going to come. These are based out of previous years and NCERT directly. Whatever is there in NCERT, CBSE syllabus, and also which was asked in previous year AIMS or NEET papers or JIPMER papers, exactly very identical questions. So we have covered till now plane mirrors and its problems. I hope you are an expert by now in plane mirrors. Are you ready to become an expert now in curved mirrors or spherical mirrors? Yes? Ready? Quickly, let's have a water break. Everybody, refresh yourself, flex your muscles quickly. do some exercise. Yeah, get up from your seat and sit down. Close your eyes, open your eyes, do the exercise. Because if you sit and stare continuously, that is also a problem, right? So quickly do the exercise, move your head around, open and close your eyes, twist your arms, everyone. Full Josh, drink some water. Okay, full of energy. Wow, very good, very good, very good. So let's talk about spherical mirrors, drawing the ray diagrams, finding the images, everything about it. Now, if I have a mirror like this or a mirror like this, these are called as spherical mirrors, but there are two different kinds depending on which side is silvered. Here the inner side is silvered, the outer side exposed is bulging out. This is then called as a convex mirror. Here it is caving. Cave means like a hole inside a mountain, right? So you can see there is a cave. The outer side is silvered, the reflecting side is in. This is a concave mirror. This is a concave mirror. Why they are also called as spherical mirrors is because if you notice, if you take any curved mirror, and you extend it, okay, extend it mentally, you will see that there is a sphere which is formed. That sphere will have a center. That sphere will also have radius. So that's why it is called as a spherical mirror. It's a part of a big sphere. This C is also called as the center of curvature. This is also called as the center of curvature, and that R is also called as the radius of what, guys? Curvature. Radius of curvature. Very good. There are more things that you should know about any curved mirror. If I divide the mirror into two equal parts, then that central point on the mirror, what is that called? Let's see how many of you know that name. What is that central point on that mirror called? Yes, my dear students, it is called as the pole. And if you draw a line which splits the mirror into two equal halves, that is called as your principal axis, correct? It is called as your principal axis. Very, very good. Awesome, awesome. So, can you also show the center of curvature on the principal axis? Why not? Can you also show the radius of curvature? Why not? So, that's how it looks like. Now, depending on the type of the mirror, it can be either converging or even diverging mirror. So, if you take a concave mirror versus a convex mirror, this is convex, this is concave, I can show the principal axis. Right? And if I show a parallel beam of light, on the concave mirror, you will see that they will meet at a point somewhere here. But if you show a parallel beam here, then they will reflect away from it. They will reflect away like this. This is a parallel beam. Here, they are basically converging. That's why it is also called as a converging mirror. Here, it is diverging. So, convex is also called as a diverging mirror. It's also called as a diverging mirror. Very good. Awesome. The point where they meet, the point in this case over here, is called as the focal point. Here, they are not meeting, so I have to extend them. I have to extend those rays, right? I have to extend the rays somewhere here. This point where I have to extend it, and then they meet, that is your F, which is your focal point. That is your focal point. From the pole to the focal point, that distance from the pole to the focal point. So from the pole to the focal point, okay, that distance is called as the focal length. It's called as the focal length. It's called as the focal length. The sign of it will be decided later on. I will tell you the sign convention, but that is called as the focal length. The symbol used is small f. Is there a relation between the focal length and the center of curvature? The answer is a big fat yes. If you see, the center of curvature will be here. In this case, the center of curvature will be here. You will see F is actually the midpoint. F is the midpoint always of the pole and whom? And the center of curvature. So that is the reason why you will see that the radius of curvature is 2 times of the focal length. This is a very, very important formula. 2 times of the focal length is the radius of curvature. 2 times of the focal length is the radius of curvature, because F is in between R or center of curvature and the pole. Is that okay? Always has to be true. Very good. Or F is R by 2, one and the same thing. Okay. Now, there are certain rules of finding where the image is. Well, there are 2 ways to find the image. To find image, there are 2 ways. One is you have mirror formulas. The second one is called as ray tracing. How many of you remember this ray tracing which you would have done back in your 10th standard? Maybe some of you also did this, but now we need to know these things. In NEET, you will need to know these things apart from the ray tracing. Go back in those old golden days when you were in 10th standard and you would have 100% done these ray tracing things. And if you want to do ray tracing, you just need how many rays? Just 2 rays. Just 2 of the rays. You just need 2 rays to form the image. One option is, if you have, for example, a concave mirror, or let's say a convex mirror, then you need a ray which goes parallel to the principal axis. After that, it passes through the focus. A ray which is parallel to the principal axis, it feels as if it is diverging from the focus. You can also show, or you can also take another ray. Which passes through the focus, but after that becomes parallel. Ray which is incident on the focus, but after that becomes parallel. This is for concave, this is for convex. This is first rule. This is your first ray which you can take. This is your second ray or second rule which you can use to find where the image is. How many of you remember these rules? Yep. Why does this happen? Because of reversibility principle of light. If I reverse the direction of the reflected ray, the ray will become incident ray. If I reverse the direction of the reflected ray, it will become the incident ray. So this is based on the reversibility principle of light. Third rule which is there. Come on, my dear warriors. Let's see how many of you remember these things back in the day. If your ray passes through the center of curvature, it will retrace back the same path. If your ray is appearing to pass or actually passing through the center of curvature, then it will retrace back the same path. This was your third rule. Yes, very good. Awesome. Yes, Sudev's plane mirror is done. you missed that part, don't worry, you can watch the lecture later on. The entire lecture gets recorded even in the live class. And the last rule is this one. Last rule is basically this one, where you show this ray which falls on the pole, it goes exactly on the other side symmetrically. If it was 30 degrees on the top, it goes from 30 degree below. Same thing over here. If it is going 20 degree from below, then it will go from 20 degree on the top, symmetrical. If it is incident on the pole, if it is incident where? On the pole. If it falls on the pole, it is a very symmetrical diagram, mirror image kind of thing. Whatever happens bottom happens on the top. These rules are enough to find where the image is for any situation. Say for example, I draw a convex mirror. And let's say this is the principal axis. Let us just say, for the sake of it, this is the center of curvature. So naturally this will become the focal point. Naturally this point will become the pole. Okay. And let's say our object is somewhere over here. I want to find out where the image will be formed. What will I do, my dear students? Start drawing the rays. You can use any of these rules for convex mirrors. These. Any rules, you will get the answer. What you will do, show let's say one ray which is parallel to the principal axis. We know that it will end up reflecting as if it is emerging out of the focal point. It will go as if it is emerging from the focal point, right? It will feel like that. That's what happens. This is one ray which I have shown. I can take any other ray, my dear students. Let's say for example, I show one ray which goes and hits the pole. What will happen after reflection? It will go symmetrically opposite like this, right? It will go like that. Extend this now, because both the rays are diverging. Where do they meet? They meet over here. Hence, this is where the image will be formed. Do you see they meet right over here? So this is where the image will be formed. By looking at this diagram, which kind of image is this? Is it real? Is it virtual? Is it erect? Is it inverted? Is it magnified? Is it same size? Or is it diminished? Try to explain the nature. What is it, my dear students? Is it real, virtual? Is it real or virtual? Come on, my dear warriors. Yes, it is behind the mirror. It feels as if the rays are coming from here. They are not actually meeting. So 100% it is virtual image. Everyone with me? Similarly, is it not of the smaller size? Hence, can I call it is diminished? Also, isn't it upright? So can I just call that it is basically erect? Can I just say it is basically erect? So that's how you get the nature of the image. Now, will you be able to do a similar thing? Even for concave mirror? 100% you will be able to do. Let us just take a random example maybe. Somewhere like this. Okay, so let's say I draw the principal axis right over here. This is your pole, and then let's say this is your center of curvature. Exact midpoint is the focal point. And let's say we take an object, maybe somewhere over here. Maybe this is an object. Maybe this is the object that we are referring to. I want to find where the image will be formed. So I can draw a number of rays. I can draw a number of rays. I have many options. And one such option is showing a ray which is parallel to the principal axis. After reflection, it will pass through the focus. After reflection, it will pass through the focus. So this is one such ray that I have shown. It is passing through the focus. Another ray that I can show is a ray which goes on the pole and reflects symmetrically, or a ray which passes through the center of curvature and rebounds on the same path. There are multiple options, my dear students. Or I can also show one ray which passes through the focus. After reflection, what happens to it is that it becomes parallel. After reflection, what happens is basically it becomes parallel, and yeah, something like this. I have not drawn it very nicely, but you can see that the image will be formed somewhere over here. It's not exactly, nice diagram because I have not drawn properly. Some of the rays are not even passing through the exact lines. Actually, it should have come slightly, outside. Yeah, slightly it should come up somewhere over here. So actually it should come somewhere here. So can you see the images? Can you see the image is what? Is it real or virtual? Is it real or virtual? Look at that. Is it real or virtual? Come on, my dear warriors. 100% it is real because it is not behind the mirror, it is in the front. The rays are actually meeting over here. Second important thing, you can see that the image is actually inverted. It's not erect, it is inverted. Can you see that? Yes, very good, very good. And also it is actually slightly of the bigger size. It's slightly bigger size. It is actually enlarged. It is actually enlarged. Okay? It is not looking that much enlarged, but it is enlarged actually. Okay? If I draw it properly, then it will come. Is that okay, my dear students? That's how you solve these questions. But this is image tracing. Will you use this method every time? No. Most of the times you will be going to the formula method. You will be going to what? The formula method. Now in the formula method, what do you need? In the formula method, what do you need? You need these three quantities. So in the formulas for spherical mirrors. Formulas for spherical mirrors. So when you do that, you need these three quantities. One is called U, which is called as the object distance. Technically, it is actually object coordinate. That is what it is. Because the moment I say distance, what comes into your mind? Scalar quantity. Distance is always positive. That's what you think, right? But although we call it as object distance, actually it is object coordinate. Can coordinate be positive, negative? Can coordinate be positive, negative? Definitely it can be both positive as well as negative, yes or no? Similarly, V is basically image distance, and this can be also positive, negative. So this is actually the image coordinate. Image coordinate. Then you have F, which is your focal length. Focal length. It is not actually a length, it is a coordinate. So it is actually the coordinate of the focal point. It is the coordinate of where that focal point is. It can be positive, negative. Lastly, you have your radius of curvature. You have your radius of curvature. It is not actually a length of radius. In fact, it is the coordinate. It is the coordinate of the center of curvature. It is the coordinate of center of curvature. Memorize this. Remember this. If these are not distances, they are actually what? Coordinates. And coordinates can be positive, negative. But when we talk about positive, negative, which direction is positive, which direction is negative? What do you guys say? Can real images be seen without the screen? Definitely, Shaku. You can see it even without the screen, but then it will hurt your eyes when you try to see a real image because it will be usually bright. If you try to see projector's image, it will hurt your eyes. You should not do that. So that's why we generally use a screen to see it, without hurting our eyes. Yep. Come on, my dear students. Which side do you take as positive? Which side do you take as negative? So we are coming now to something called as the sign convention. Something called as the sign convention. So as per the sign convention, it so happens that be it concave or be it convex, really doesn't matter. Actually, 1 second. Both of them are concave now. Both of them are convex right now. Okay. Which side is positive? Which side is negative? Is it left or right? Behind the mirror, front of the mirror? That is wrong. See, that is why you might make mistakes in the examination. Don't do all these things behind, front and all that. It all depends on, see, many people have learned it the wrong way. Positive, remember just this, positive is always in the direction of incident ray, and also positive is also upwards. Upwards is positive, that is standard. But in the horizontal direction, it's always in the direction of the incident ray. Where is that incident ray? That's what decides everything. If there is an object here and the incident ray is going like this, maybe reflecting somewhere, the reflected ray might go anywhere. Where is the incident ray going? Like that. Like that. So always remember, your pole becomes your origin. Pole becomes your origin. Pole becomes your origin. Pole becomes your origin. And whichever direction the incident ray is going, that side, which direction? Arrow mark. Check the arrow. Not where it is. The arrow mark where it is pointing. Where is that arrow pointing? Right side. So hence, this will be the positive side. This will be the negative side. This will be the positive side. This will be the negative side. Here, if the ray is coming like this, and let's say it is going like that, okay, this is the incident ray. The incident ray is pointing towards this side. So this will be positive side. This will be the negative side. This will be the positive side. This will be the negative side. In this case, if, for example, the ray is coming like this and going like this, this is the direction in which the incident ray is going. So it is pointing towards the right side. So this will be positive side. This will be negative side. If there is a ray which is coming like this and going like this, incident ray is pointing this way. So this side of the mirror is positive. That side is negative. Is that very, very clear? Is that very, very clear? So it's not right, left. It's on the direction of the incident ray. And this sign convention is not just for mirrors, but it's also for lenses and anything else. So, my dear students, if I ask you, what about the, what about the focal length and the radius of curvature? What about the focal length and the radius of curvature? Is it positive or negative? What about the focal length and the radius of curvature? What about the focal length and the radius of curvature? In each case, is it positive or negative? Come on, fill up the answers. In this case, where is the focal point going to be? It is here. Where is the center of curvature going to be? It is here. And what did I tell you? For everything, always check the coordinate of focal point and center of curvature. Isn't the focal point and the center of curvature both on the negative side? So won't this be minus, this also be minus? Here also, the focal point and the center of curvature. focal point and the center of curvature are on the negative side. So won't this be negative? Focal length and the radius of curvature. So can I then generalize? For concave, focal lengths are negative. For concave, focal lengths are negative. Exactly. Very good. Check it for convex. Where is your focal point and center of curvature? It is here. It is on the positive side. So this is positive. Here, check it out clearly. Again, it is on the positive side. Very good. Focal length is on the positive side. Very nice. Now, there is one more thing which I need to tell you. Where did it go? Yeah, over here. When a mirror is curved, either it converges or it diverges. How quickly it converges or how quickly it diverges decides something called as the power of the mirror. What does it decide? Power of the mirror. So on this slide only, maybe I can put up a diagram. Let's say there is a mirror here, and let's say there is a mirror like this, and here the rays meet like that, and here the rays meet like this. Compare these two mirrors and tell me who has more focal length. Who has more focal length out of these two? If I call this as mirror number 1 versus mirror number 2, whose focal length is more? Whose focal length is more? Focal length of mirror 2 is more. Magnitude wise, focal length of mirror number 2 is more, yes or no? So over here, aren't the rays converging slowly, aram se, coolly, after taking some time? Here they are converging very quickly. So can I say this is more converging, this is more converging, and this is less converging? This is less converging, this is more converging, this is less converging. So less focal length is more converging, more focal length is less converging. Getting it? Getting it? Everybody with me? 100%, yes. So that means the power of mirror number 2 magnitude wise is less than power of mirror number 1. Power of mirror number 1 is higher power and power of mirror 2 is lower. So we define this quantity called as the power of a mirror. So power of a mirror is the degree of convergence or divergence. Degree of convergence or divergence. The power formula, check this out over here. This is a concave mirror. This is a concave mirror. So for this, focal length will be positive or negative? Focal length will be positive or negative? Focal length is a negative value. We just saw that in the sign convention. But when a mirror is converging, then we say that the power is positive. If the mirror is diverging, then we say the mirror is, the power is negative. So keep these things in mind. When you have a concave mirror versus a convex mirror, so for concave, the power is said to be positive because it is converging, but for a convex mirror, the rays diverge, so the power is said to be negative. So observe carefully now, my dear students. For concave mirror, focal length is negative, but power is positive. For convex mirror, focal length is positive, power is negative. So shouldn't they always be of opposite sign in case of mirrors? If this is positive, this is negative. This is positive, that is negative. Aren't they of the opposite signs? Very good. So when I write the power formula as 1 by f, because more focal length is less power, you saw that here. More focal length is less power, less focal length is more power, but signs are opposite, so I put a minus sign over here. This is the formula for power. This is the formula for power. Is that okay, everyone, till this point? Amazing. And keep this in mind, if F is in meters, basically SI unit, then power is in diopters. Power is in diopters. Keep this in mind. So just to give you a simple example before we go ahead, tell me guys, in this question, a convex mirror of radius of curvature 40 centimeters has focal length of and power of. Has focal length of and power of. Come on, my dear students, try to solve this question. I'm waiting to see all your answers. Come on, let's see how many of you are active. Let's see how many of you are active. Come on, my dear students, think. We know R is basically 2F, radius is 40, but since it is a convex mirror, remember center of curvature and the focal length both will be on the positive side, not on the negative side. So this is actually plus 40 is 2 into F. So F will be plus 20 centimeters. This is the first answer. But always keep focal length in meters if you want to find power. So it is 0.2 meters. So power, which is minus 1 by F, which is minus 1 by 0.2, won't it be minus 5 diopters? Minus 5D diopters. Yes. How many of you wrote minus 5? Yes. Minus 5, not plus 5. Don't write plus 5. If you write plus 5, you will get negative marks. You have to put the minus sign. What does this minus sign indicate? It just says that it is diverging in nature. It just says that it is diverging in nature. Nothing more. Very good. Awesome. So now, if you are given a mirror, using mirror formula, can I find the location of the object and the image? The answer is definitely a yes. The answer is definitely a yes. And what is the mirror formula? What are those mirror formulas? Let's have a look at it. Mirror formulas. The first mirror formula is 1 by V plus 1 by U is equal to 1 by F. 1 by V plus 1 by U is basically 1 by F. This is the first formula. The next formula is for how much is it magnified or how much is it diminished. So we'll talk about magnification. What is the meaning of magnification? And then I'll put it on that slide. Magnification. Just like we saw what power is, let's also learn what is magnification. If there is an object over here and let's say the image becomes larger, then I will say that the magnification is more than 1. Then I'll say the magnification is more than 1. But let's say, for example, the object is like this and the image is even smaller. Then I will say the magnification is less than 1. And if it happens that whatever that object size is, the image is also of the same size, then I will say that a magnification value is equal to 1. It is equal to 1 magnitude wise. Did you understand what does magnitude tell you? Whether it is big, small or of the same size. Similarly, if the object is like this and the image is inverted, then the magnification, or let's say we start with first like this. If the image is of the same direction, then the magnification is said to be positive. And lastly, if object is like this, but image is exactly opposite, then the magnification is negative. So the sign tells you whether it is erect or inverted. The magnitude tells you whether it is enlarged or diminished. For example, if I tell you the magnification is 0.2, what can you tell about the image, my dear students? Because it is in decimals, 100% it is diminished. 100% it is diminished. Because it is positive, that means it is erect. Similarly, if I tell you another example, magnification is minus 1.5. Minus 1.5. From this, what can you tell? Forget the sign. Magnitude is more than 1. So 100% it is enlarged. It is enlarged. And because of the negative sign, it means it is inverted in nature. Similarly, if I by chance tell you magnification is plus 1, then what can you tell? Because the magnitude is 1, that means it is of the same size. It is of the same size, and because of the positiveness, it is erect. Is that right? Very good. Awesome. So that is basically your magnification. Magnification is height of the image upon height of the object, or the image size by object size in general. I would just say magnification is image size by your object size. Now, this magnification are also of two types. Not many people know this. This magnification is also of two types. One is longitudinal and lateral. One is longitudinal, other is lateral. What is the meaning of lateral magnification? What's the meaning of longitudinal magnification? See, my dear students, if this is your principal axis, there is a mirror here, doesn't matter which kind. So it could be concave or convex. It could be concave or convex, really doesn't matter. Point is that if it is lateral magnification, what I am referring to is, let's say this is image, an object. So, in case of lateral magnification, basically this is also perpendicular, meaning perpendicular to the principal axis. Perpendicular to the principal axis. So, if this is the height of the object and this is the height of the image, then height of the image divided by the height of the object, that will give me the lateral magnification. Sometimes I use this symbol just to show that it is in the perpendicular direction to the principal axis. Height wise, how much did it enlarge? Height wise, when you stand in front of the mirror, your height might become big or small, especially if it is a curved mirror. Your body size might also become wide or thin. That is longitudinal. Long, along. Long, along. Along whom? Principal axis. So it is along principal. Along the principal axis, or basically parallel to it. So if I show this as the width of the object, and if I show this as the width of the image, so width of the image upon the width of the object, that gives you the longitudinal magnification. Is the difference very clear? Is the difference very clear? How many of you did not know this till now? How many of you had just by-hearted the formulas, but maybe today finally you understood the difference between lateral and longitudinal? Lateral and longitudinal. Lateral is perpendicular. Long, along parallel principal axis. So that will be the width along the principal axis. This is height perpendicular to the principal axis. Is that right, everyone? Understood or clear? Yes. You had just by-hearted, Sarath, now you understood. Janice had known it from before, very good. Some of you, probably my old students, might know it, but yeah, this is what it is. So now going to the formula right over here, what are the mirror formulas? If you talk about the lateral magnification formula, which is height of the image by height of the object, that is minus of V by U. That is minus of V by U. You should know this. Negative sign is very important. Don't forget that. But if you talk about the longitudinal magnification, which is width of the image upon width of the object, then minus sign is again there, but you divide V with U and then whole square it. V with U whole square it. Minus sign is outside the square, because if you put it inside, squaring it will make it positive anyways. Then there is no point. So it's outside the square. Keep this in mind. This is very important. Cool. Now, do you also remember that I had given you a formula for plane mirrors? If object moves, how much will be the velocity of the image? Do you remember that? If object moves, what is the velocity of the image? I had given you a formula, yes or no? So, is there a formula for mirrors too? Answer is yes. Answer is yes. If the object moves with a velocity of VO and then the image moves with a velocity of VI. So what is VO and VI? This is velocity of the object. This is velocity of the image. Then it so happens that if you divide velocity of the image upon velocity of the object, you get the exact same value over here, which is this one, which is basically this one. So my dear students, you can just extend this formula of longitudinal magnification. It is also velocity of the image upon velocity of the object. Isn't this fancy? This is like all the formulas on one slide. And one last formula which I had already given you, power is minus 1 by f, that I had given you before only when I explained you what power is. So these are the only mirror formulas which you are going to need. These are the only mirror formulas which are going to need. And before that, I had also told you R is basically 2f. R is basically 2f. That also I had given you. That's all you are going to need. Take a screenshot, put it up in your notes. That's all you need, my dear students. Shreyas Sir's notes, more than enough for cracking NEET. Shreyas Sir's notes, more than enough for cracking NEET. And I can guarantee you will get 180 marks. Yes. Shall we do some questions? All the slides I have kept it as it is. You are going to get the notes in the Telegram channel. Remember that. Cool. Everything I have explained you in detail. Everything is in detail right from the scratch. So even if today a 10th standard student is watching this lecture, I don't know if you are a 10th standard student, but I think even that student will be able to understand this class. That simple I have made it. Already written, very good, Sarath. Let's go to the questions part. The field of view is maximum for whom? Field of view is maximum for whom? Concave, convex, plane, parabolic, concave mirror. This is a GK question. In the parking lot, you see that there are mirrors so that you can be aware of the surroundings and if somebody is coming from, some other side. Even your rear view mirror of your car or your bike is of a particular type. It bulges out. Why? Because it has a big field of view. Yes, so that is convex mirror. Exactly, convex. Concave is like this. Concave is like this. It is having a small field of view. Convex, it bulges out. It has a large field of view. Correct. Plane mirror, it's just flat like that. Correct? Okay. The diameter of a concave mirror is 20 centimeter, the diameter of curvature actually. Then the focal length is the diameter of curvature of a concave mirror. The diameter of curvature of a concave mirror is 20 centimeters. Then the focal length is, come on my dear students, diameter is given. So what will be the radius? Radius is diameter by 2 magnitude wise. Magnitude wise, if you talk about it, it is 20 by 2, that means it is 10 centimeters. But which mirror is it? It's a concave mirror. So technically speaking, the radius will be minus 10 centimeters since negative for concave. We have discussed this in detail. So next, what is focal length? Focal length is r by 2. So minus 10 by 2. So focal length is minus 5 centimeters. Is it there in the options? Definitely. 2. B. Yes, B for bananas, 2 minus 5 centimeters. B for biology. Yeah, perfect. See, the love for biology is coming up. All those students, you have now amazing master teachers. They are very passionate, be it Gopika ma'am or Baswa sir, amazing teachers. And they relate very well with students because they are young and dynamic personalities. And that's the reason why we have such amazing teachers in the, NEET Warriors team. Because we want to make sure that the students are very comfortable. They feel like our teachers are like friends whom they can connect with very, very easily. So my dear students, if you are thinking of learning for NEET, be it physics, be it biology, be it chemistry, this is the only channel. This is the only channel because we go very slowly, very systematically from NCERT with PYQs and everything that is needed for NEET. No shortcuts, no long cuts, the right way. Moving on to the next question. Person sees his virtual image by holding a mirror very close to the face. When he moves the mirror away, the image becomes inverted. Which kind of mirror do you think this is? Which kind of mirror is this? Thank you, Sarat, so much. Yes, Janice, the superb teachers. The rear view mirror is first and not bulged out. Why is it so? No, Shaku, it is actually bulged, but the bulging is so less, you feel as if it is flat. There is a small bulge, very difficult to feel it, but it is there. The mirror is only so small, very difficult for you to feel the bulge. Yes. Come on, my dear students. What do you think? 100% convex mirrors always give you erect, diminished images. Erect and diminished images. But when you talk about concave, then it can be erect, it can be inverted, it can be enlarged, it can be of the same size, it can be even diminished, it can be real, it can be even virtual. All this depends on the positioning of the object. You can draw the ray diagrams at different locations. You will see the size will change, inversion will change, all those things. So hence it has to be a concave mirror. Concave mirror is the mischievous mirror. Convex is power mirror. Power mirror because only it shows erect, diminished images. No matter where you are, it will always show you erect and diminished images, which are also virtual in nature. Okay, erect, diminished, as well as virtual. You can take a spoon and do it. From this side, you will see all crazy things. From bulging side, convex side, Always small chintu mintu images you will see. Chintu mintu images you will see. Very good. Exactly. Hello Sparkle, nice to see you after a very long time. Moving on to the next one on your screen. Object is this tall and it is placed 1 meter from a concave mirror which has some curvature. The size of the image, is it inverted or erect? Okay. So let's draw the diagram. It will be very easy. So you draw a concave mirror. Okay. Object is 5 centimeter tall. Radius is given. Placed 1 meter. So the object which is 5 centimeter is placed at a distance of 100 centimeter right from here. Since the radius is minus 20 centimeters, f which is r by 2 will be minus 10 centimeters. Now obviously for concave mirror, this is the negative side, this will be the positive side, this will be the origin, correct? The incident rays will be going like that, that is positive, this is negative. So my dear students, what are we going to do? What are we going to do over here? So use the mirror formula. 1 by v plus 1 by u is 1 by f. 1 by v plus 1 by u is minus 100, is minus 100. F is minus 10. So 1 by v is equal to, take it on the other side, it will become plus. So 1 by 100 minus 1 by 10. Taking the LCM which is 100. So it will be 1 minus basically 10. So it will become minus 9 by 100. So v will be negative 100 by 9. Negative 100 by 9. But that's not the question. The question is, what is the size of the image? So we use magnification formula. Oops. Magnification formula, which is minus v by u, which is height of the image upon height of the object. V is minus 100 by 9. So minus 100 by 9 divided by u is minus 100. U is minus 100. Minus 100 cancels. So it will become minus 1 by 9. So height of the image will be minus 5 by 9 of a centimeter. 5 by 9 of a centimeter, check that out, it will be minus 0.55 centimeter, recurring decimal. Size wise it is C. Size wise it is C. Just check that out. Size wise it should be C. Awesome. Awesome. Very good. Awesome. Moving to the next one. Point object is going along the principal axis of a concave mirror. Focal length 24 towards the mirror. When it is at 60, then its velocity is 9. What is the velocity of the image at that instant? Interesting. Image velocity question, what do you need? You need image distance and object distance. Do I know the object distance? Yes. But is this plus 60 or minus 60? You are in front of the mirror, so I think it will be minus 60. Which mirror it is? Concave. Concave means negative focal length. So is this focal length plus 24? No, that focal length will be minus 24. Focal length will be minus 24. So let's use mirror formula and see what do we get. 1 by v plus 1 by u is equal to 1 by f. 1 by v plus 1 by object distance minus 60 is equal to 1 by minus 24. So therefore 1 by v is 1 by 60 minus 1 by 24. Taking LCM, LCM will be 120. This will be 2 minus 5. 24 5s are 120, 62s are 120. So this will become minus 3 by 120, which is minus 1 by 40. So therefore, the V value will be minus 40 centimeters. But that's not the part. The part is you have to find velocity of the image. So velocity of the image by velocity of the object is minus of V by U whole square. Image velocity I don't know. Object speed is given 9 is minus V by U. V is minus 40. U is minus 60 whole square, which is 2 by 3. whole square, which is 4 by 9. 4, this minus sign comes here. 9 cancels. So in the next step, velocity of the image is minus 4 centimeters per second. So magnitude wise, it is 4 centimeters per second. Because it is minus, it is going towards the mirror. How do I know that? See, this is the mirror. This is the mirror. Like this. Okay. Or is it going away from the mirror? I think it is going away from the mirror. My bad. It is not towards the mirror, because see where the image distance is. It is minus 40. Image is at minus 40. That means this is where your image is. This is negative side. This is positive side. Image velocity is minus 4. Image velocity is minus 4. That means it is going like this. 4 centimeters per second. It's going away from the mirror. It's going away from the mirror. If it was plus, then it is going towards the mirror. So accordingly, we will change the answer. Yes, awesome. So before going to refraction, I think we'll take a small break. But till now, are you clear about it? Let me put the break slide where it is. I put one nice, beautiful break slide. Oh my God. Okay. So I planned for a break much later, but looks like we have taken nice amount of time. So shall we take a break? Yeah, till now everything clear. If it is clear, put up a thumbs up, smash the like button, and if you're watching it recorded, I hope you are commenting as well. Okay, so we'll take a short break. Right now it's 8:30. I think we'll meet at 8:50 p.m. What say? Let's meet and let's see how much of the chapter we'll be able to complete. If not, we'll have a part 2 also of the class. Don't worry. Okay, we'll try to complete as much as possible. Okay, see you guys, and make sure you're liking, and remember that hashtag which you need to comment, WPWP. That's your hashtag. Do not forget to like. Do not forget to like and also comment. Okay, I'll see you in a bit. Yo, break time is over. Get back, get back, get back, my dear students. Come on, let's freshen up. Let's come back. Let's energize. Let's get back to the session. By the way, I'll be breaking this session into two parts. Today, I will be just doing till refraction because, you know, I have taken it in a very systematic and very, I would say, in a very easy manner so that every student understands it. So I think it's okay. We are not in a hurry to complete everything in one lecture. Even if it takes 2 classes to complete a topic, I'm perfectly okay. So I'll be taking the part 2 next week. The exact date and time will be put up in the schedule, in the timetable as well. Okay. So is that okay? Is that fine, everyone? Let's do till refraction today. Refraction, apparent shift and all of that. We'll do that today. And the lenses, curved surface refraction, combination of lenses, prisms, and also the optical instruments part. That part we'll do it in the next lecture, which is completely based on refraction. Okay, application. So today we'll do plane surface refraction. Let's get back. Come on, call all the students. Sometimes students just go after the break and they're like, okay, done. I forgot only about the class. Don't do that. Post it in the Telegram. Post it for your contacts. Let your friends know Shreyas Sir is back for refraction. So let's get ready. All right. Yes, Sanvi says okay. Sarath, my health is fine, but just that I'm feeling very tired because I was doing some recordings and all that. By the way, tomorrow there is going to be a very interesting session. I don't know how many of you have seen it, and if you are going to watch this class recorded, watch this class at least recorded. Yeah. Oh my God, I really love this thumbnail. I don't know how many of you have seen this. Look at it, very cool thumbnail. Already smash the like button, please. Yeah. See the funny side of the teachers. We have some fun games for all of you. We'll all play with each other. And hopefully you will be in one of our team. We'll probably have some teams and we'll play some really cool things. So tomorrow at 7 o'clock on Saturday. I mean, it's that time of the year where, you know, the year is ending. Everybody is, you know, trying to relax, trying to gather themselves up and trying to prepare themselves for the next year. So I think we should, you know, casually talk also and motivate and, you know, also get to know each other really well. So why not? You know? So see the funny side of all the teachers. Tomorrow, smash the like button already. Let me see this go up till 100 at least before the session starts. So before the session starts only, it should go at least 100 likes. Then we'll start the session, or else we'll not start. Okay. So let's do that tomorrow. And yes, please make sure that you are also checking out the description box of every video. Not only is the Telegram link over here, but also 7 years PYQ quiz. 7 years PYQ quiz link is also here. This is like your DPP. Just enter your details, you are done. And there is a mock test coming up this Sunday. Mock test coming up this Sunday. So make sure you click on this link and attempt that mock test. Okay, it's a free mock test from NEET English channel, your Vedantu NEET English channel. So 3 free things. One is your Telegram group for PDF notes and other quizzes. Your DPP attached here, and also the weekly mock test attached right over here. So many things that you get on this channel, guys. I mean, I don't think any other NEET channels do this. Very few channels. There are channels, there are very few channels, English channels, so don't do this. Only it's us who do so many things for you. So please show your support, please show your love. It means a lot. Yeah, I know. Everybody is looking very, very funny. I think only Gopika ma'am is looking perfect over there in that cartoon thumbnail. Hai na? I don't know. We are looking out of the box. Anyways, so let's start with refraction. Let's start with the refraction over there. So, refraction, just like reflection rebounds the light, reflects the light, refraction bends the light. So, it's the bending of light phenomena. So, bending of light due to medium change, due to the medium change is called as refraction. But there is one thing which does not change in the refraction, and that is the frequency. The frequency of the light remains unchanged. the frequency of the light remains unchanged. Unchanged. It remains the same. It does not change. Keep that in mind. If it is yellow light, it remains yellow light. If it is green light, it remains green light. If it is purple light, it remains purple light. Yep. Okay. Okay. Yes. Then next thing that you should know is the speed and the wavelength change. Speed and the wavelength change when the medium changes. When the medium changes. When the medium changes. There are many examples of refraction, like bent spoon in a mug filled with water. Filled with water. You might have seen this. Or even lenses. Lenses are because of the refraction phenomena. Also the concept of apparent depth. Apparent depth is because of refraction. Even the twinkling of stars. Even the twinkling of stars. How many of you knew this? A lot of you see the stars in the night sky and you see them twinkle. That means they become dim, bright, bright, dim, alternatingly. Why does that happen? Is it that somebody is lighting the fire and turning it off and then turning it on again and turning it off? No. It's because refractive indices of the atmosphere keep changing. Why? Because wind is blowing, clouds are there, atmosphere changes happen. So when the atmospheric changes happen, the light which is entering the atmosphere sometimes goes this way, sometimes goes that way, sometimes goes this way. So that atmospheric effects is what causes the twinkling of the stars. So if there was no atmosphere, I don't think we would have twinkling of the stars. Yep, we wouldn't have twinkling of the stars. Yes, so many examples are there of refraction, my dear students. So let's start seeing the formulas. And let's start also seeing some special things. So if this is a interface and this is your normal, this is the interface, this is your interface, this is medium number 1, this is medium number 2. So your light might enter like this, might go like that. This is your incident ray, this is your refracted ray, this is your angle of incidence, this is your angle of refraction, this is your angle of refraction. Your speed of light here might be c1, your speed of light here might be c2, c1 by c2, c1 by c2 is going to be a constant, c1 by c2 is going to be a constant, and that constant is called refractive index. That constant, what is it called? Refractive index. Exactly. Now, how you label this constant is, see which medium to which medium it is going. Where is it going from? Medium 1. To which medium? Medium 2. So 1 to 2. 1 to 2. Have you seen the symbol of Amazon? Amazon. Everybody might have ordered some or the other thing. Dress, some, charger, mobile, power bank, something. It goes like this. You know why that symbol is there in Amazon? How many of you know the significance of this arrow mark? How many of you know the significance of this arrow mark in Amazon? Let's see. Oh, we have Vaswa Sir too. I hope, Vaswa Sir, you had your dinner. Just like our students, they have dinner within 20 minutes because they know we teachers, we come back within 20 minutes and we start our classes in the break. Long marathons. A to Z. Yeah, it's basically you get A to Z things. A to Z things. You ask for apple also, you will get it. You ask for zebra also, you will get it. Just kidding, guys. Don't order zebras through Amazon. Okay. So over here, it's going from 1 to 2. So 1 to 2. 1 to 2. That's how the light is going. No need of the arrow mark. This is just to show how it is written. And it is also equal to sine of angle of incidence I upon angle of refraction, sine of r. This is basically called as your Snell's law. This is basically called as your Snell's law, as simple as that. Something which you should remember, of course, something which you should remember, yep, like this. Now we also know one more thing, speed of light is frequency into wavelength, and it was the frequency which remains unchanged. Frequency remains unchanged. So if I write C as f into lambda, ff cancels, lambda remains, so it will be lambda 1 by lambda 2. So that is also 1 mu 2. That is additional relationship in certain problems which we will be needing. Yep. Another thing which you should know, what is this refractive index dependent on? What is this refractive index dependent on? So refractive index. When I say 1 mu 2, that means where is light going from? Light goes from 1 to 2. But when you pronounce, when you say it as refractive. You say it as refractive index of 2 with respect to 1. You say it as refractive index of 2 with respect to 1. So for example, if I say refractive index of donkey with respect to zebra, that means my symbol should be mu, refractive index of donkey with respect to zebra. So just flip it. So zebra will come first, donkey will go next. Where is the light going from? Light is going from zebra to donkey. Light is going from zebra to donkey. But while saying it, you say it opposite. Is that clear? No, it's not about rare dense, Bikaron. It's not about rare or dense. It's about the order in which you write it via convention. These are just conventions, historical conventions. That's it. This is also 1 mu 2 is also, this is your relative refractive index. Okay, this is relative refractive index. It is mu 2 by mu 1. Mu 2 by mu 1. Also, it is reciprocal of 2 mu 1. 2 mu 1. Reciprocal of this. Very, very important formula. Very, very important formula. If you notice carefully, this one and this one, they are relative refractive index. Relative to something. But if you notice this one and this one, they are absolute refractive indices. These are absolute refractive indices. These are relative to something. In absolute, you do not see any other number here. You do not see any other number here. So absolute are with respect to whom? With respect to vacuum. With respect to nothing. With respect to vacuum. So absolute refractive indices are expressed when light is coming from vacuum into the medium. Maybe vacuum to glass, maybe vacuum to water, maybe vacuum to glycerin, maybe vacuum to flint glass, maybe vacuum to oil. So that is when you use absolute refractive indices. Is that clear? Understood? So what are some values of refractive indices? Oh, by the way, if I tell you refractive index of donkey with respect to zebra, it is 1.7. If I tell you it is 1.7, then refractive index of donkey with respect to zebra is 1.7. Then refractive index of zebra with respect to donkey will be how much? Come on, put it up in the chat box. Refractive index of zebra with respect to donkey will be how much? Come on, my dear warriors. Thank you, Baswa sir. Yes, warrior Pandu, Visalpudu is the meaning of WPWP. All the warrior Pandus are over here. And when they watch all these classes, Just like the CSK team tagline, we cheer them up, we whistle for them. Just like when Rajnikant comes, or when KGF starts, or when Ram Charan Sir comes, right? On the screen. So we whistle. That's how we do it. Yes, 1 by 1.7. I was waiting so long. Okay, 1 by 1.7. Correct. So what are some examples of absolute refractive indices? Let's say refractive index of glass, that is on an average 1.5, or basically 3 by 2. Refractive index of water, refractive index, this was glass. Refractive index of water is 1.33, which is nothing but 4 by 3. Refractive index of diamond, refractive index of diamond is approximately 2.4. Refractive index of air is almost 1, which means you can treat air is just like vacuum. It's slightly more than 1, but it is almost 1. So it is like vacuum. Is that okay, my dear students? Is that okay, my dear warriors? So, say for example, I ask you this. What is the refractive index of glass with respect to water? What is the refractive index of glass with respect to water? I just gave you a formula right over here. 1 mu2 is mu2 by mu1. 1 mu2 is mu2 by mu1. Use this formula. I think you shall get it. 1 mu2 is mu2 by mu1. So it is mu g by mu w. Do I know mu g? Yes, it is 3 by 2. Do I know mu w? Yes, it is 4 by 3. Oops. Once again, yeah, 4 by 3. So what will it be? 9 by 8. So 9 by 8 is the answer. How many of you wrote 9 by 8? How many of you wrote 9 by 8? Proud of all of you. Yes, that's how you find it out. So you find it out with respect to anything. It's very, very straightforward. Okay, this is the formula that we use. This one. 1 mu2 is mu2 by mu1, which is a reciprocal of 2 mu1. Okay, till this point, did you understand what is Snell's law? It tells me that there is a constant. That constant depends on both the mediums, on this side and that side of the interface, which is the ratio of the speed of light in the first medium upon the speed of light in the second medium, which is also sine of the angle of incidence upon sine of the angle of refraction. Speed of light is f lambda, ff cancels, it's also lambda 1 by lambda 2. And relative is always something with respect to something, but absolute is always with respect to vacuum. Some values which we need to remember is over here. For glass, water and diamond, and air is as good as vacuum. There is hardly any change. So now, my dear warriors, if I take two different scenarios, let's say there is air over here, let's say there is water over here, let's say there is glass over here, let's say there is air over here. Okay, these two scenarios completely different. Let me draw how the incident ray will look like. Come on. If the light comes from air into water, it will bend towards the normal. But if it goes from the glass to the air, it will bend away from the normal. This is I. This is your R. You can see that here R is more than I. Here I is more, R is less, I is more than R. Correct. So it bends towards the normal when you go to a denser medium. I can say this is denser medium. Optically, this is rarer medium. Now a lot of students think when I say optically denser, they think, so density of water 1000 kg per meter cube, density of air 1.29 kg per meter cube. Are you talking about that density? No. That density is actual density of mass per unit volume. No. This is basically optical density. Optical density means, forget the units, there are no units and all, it's just a relative term. If it is denser, it just means the light bends towards the normal. If it is rarer, it just means the light goes relatively away from the normal. That's all. Here, in case from rare to dense, will the speed of light increase or decrease? Speed increases or decreases? Put it up in the chat box, then we'll discuss this one. What will happen to the speed? You're going from rare to dense, from vacuum to water, air to water. What will happen when you go to dense medium? The speed of light will decrease. The speed of light will decrease. Whereas here, you're going to a rare medium, speed of light increases. Correct. If you talk about wavelength, we just saw what happens to the wavelength. Where is it? Yeah, on this slide. C1 by C2 is lambda 1 by lambda 2. If C1 increases, lambda 1 increases. If C2 increases, lambda 2 increases. So, C and lambda are proportional to each other. That just means if C decreases, lambda decreases. If C increases, lambda wavelength will also increase. Clear? Everybody with me? Understood both these cases? One is rare to dense, one is dense to rare. Awesome. So I think it's a good time that we start solving some basic questions. The velocity of light in air is c, which is 3 into 10 to the power 8. You should know the value of c, which is 3 into 10 to the power 8 meters per second. What is the speed of light in that medium whose refractive index is 1.4? This is a JIPMER question. This is a JIPMER question. Yep. Yes, like the cars get near in traffic jam. Yeah, Janice. Correct. Dense. The cars come close. Correct. So, is there a way to solve this? Speed of light in air upon speed of light in the medium. It has gone from air to the medium. Is refractive index of that medium with respect to air, which is just the refractive index of the medium. So hence, the speed of light in that medium, take that on the top, mu comes below. Speed of light in air, air is as good as vacuum. Air is as good as vacuum. So it will be C divided by the refractive index. Is that right? So therefore, speed of light in that medium will be 3 into 10 to the power 8 divided by 1.4. When you do the math, how much does it come out to be? 3 divided by 1.4, it will be, come on guys, it will be slightly more than 2. It will be slightly more than 2. Yes, 2.1. It will be slightly more than 2. So 2.1 into 10 to the power 8 meters per second. Right? Everybody with me? Yes. Awesome. Not 0.2. It will be slightly more than 2. That's why 2.1. Cool. Moving on to the next one. Absolute refractive indices of glass and water are this much. Ratio of velocity of light in glass and water. Just like the previous question. Ratio of speed of light in glass upon ratio of speed of light with water. CG, just like over here, where did it go? Speed of light in any medium is C divided by refractive index. C divided by refractive index. So why not use that? C divided by refractive index of glass. C divided by refractive index of water. CC got cancelled. So mu W went on the top. Mu G came below. What is the refractive index of water? It is 4 by 3. What is the refractive index of glass? 3 by 2. So 4 into 2, 8. 3 3s are 9. So 8:9 should be the answer. Just check this out. Yes, option number 3. Very good, Amit. Hello, Soumyadeep Bomik. Yep. Is that right? Everyone understood what we did? We just use this same thing, what we did here, analysis. Speed of light in any medium is C by mu. That's what the formula we have used. So speed of light in any particular medium is speed of light in vacuum divided by the absolute refractive index of the medium. That's all I have used and substituted the value. Cool. Let's do one more question before actually going ahead, which is out of my interest. If reflected and refracted rays are perpendicular to each other are perpendicular to each other. Find relation between angle of incidence and the refractive index. Find the relation between angle of incidence and the refractive index. Ready to solve this? Okay, chalo, let's see. I think we have Gopika ma'am too in the class. Hello Gopika ma'am. See, all bio students attending physics lectures. If bio teachers can attend physics classes, come on NEET students, you have to crack physics, and only then you can crack NEET. You have to crack all the subjects. And many students think, sir, physics, can I leave it as an option? One student asked me that. Sir, I will score 360 out of 360 in biology, 180 out of 180 in chemistry. Wow, very good. So if you are so intelligent to score 360 and 180 in bio and chem, why not score at least 120, man? You will get aims at least. Somewhere close to some, a good rank you will get. So guys, you cannot leave anything as option, right? Thank you so much. Yeah, we will crack it. Yes, Shivani. So how about solving this question, my dear students? This is the interface. This is the normal. What exactly is happening? This is the incident ray. This is the reflected ray. This is, oops. My God. And this is the refracted. Wait a minute, I'll draw it again. This is the incident ray. This is the reflected ray. And this is the refracted ray. Okay, it could be anyhow. It could go towards or away. It doesn't really matter. That's not the point. So if this is angle of incidence, won't this also be the angle of incidence? Think about it, because reflection, right? This is reflection, so they both will be equal. This is the refracted ray. I don't know how much is this R, but I'll just keep it as it is. Now, according to Snell's law, refractive index is sine of I by sine of R. Question says, find a relation between I and mu. I and mu. What is this guy R doing over here? I want to get rid of this guy R. Let's get rid of this guy R. How do we get rid of this guy R? How do we get rid of this guy R? Let's use some kind of geometry. Observe carefully now. Observe carefully now. You will notice that this angle is 90 degree. Out of that, this angle is I. That means how much will this angle be? How much will this angle be? Won't it be 90 minus I? 90 minus I. Everyone with me? Very good. It's clearly mentioned reflected and refracted rays are perpendicular. Reflected and refracted rays are perpendicular. That means this is 90 degree. That means this is 90 degree. Oh, so if this is 90 and this is 90 minus I, naturally this must be I only, no? This must be I. If this is I, then if this is I, only then this will be 90 minus I. Agree or disagree? Got it? Because these both are perpendicular to each other. Okay, if this is I and I know this is 90 degree, if this is I and I know this is 90 degree, so what is this R going to be? Won't this R be equal to 90 minus I, my dear students? Won't it be 90 minus I? How many of you understood this logic till here? Very good. Good evening, everyone. Joining in late, no problems, but watch it. So this will be sine of I by sine of R. What is R? R is basically 90 minus I. What is sine of 90 minus theta? Sine 30 is cos 60. Sine 20 is cos 70. Basically, sine of 90 minus I is cos of that I. It's basically cos of that I. And what is sine I by cos I? It is nothing but tan of I. So mu is nothing but tan of I. We got it. What a brilliant question. This kind of question has come many times in your NEET. This kind of question has come many times in your NEET examination. Cool? You solved this question. You should be proud of it. Let's move to the next question coming up on your screen. But for that, we need to know apparent shift and total internal reflection, all of this. So here is a scenario to understand total internal reflection. Take this scenario where this is the interface, this is the rare medium, this is the dense medium. Okay, and let's say for example, you are passing the light at a very small angle, let's say like this. So because you're going from dense to rare, it will go away from the normal. That means you will go like this. Okay, cool. Now slowly I increase the angle of incidence. I make the angle of incidence go little higher. So it will bend even more away from the normal. It will go even more away from the normal. Now, when this is happening, please remember the light is not only coming out, but it is also getting reflected. This light partially goes out, partially comes in, just like in this particular problem. In this particular problem, the light not only went to the other side by refraction, but it also got refracted. And it happens very commonly. You are seeing outside through a window. You can see outside, but at the same time, you can see a faint reflection of yourself on the window. Sometimes there are mirrors through which you can see yourself, and they are also transparent little bit transparent. So that is why I'm saying when light goes and to other medium, not all of it goes to the other medium, a part of it might be reflected. So same way over here also, isn't it true that a part of this light might be reflected? A part of this light might be reflected. Even this light which came out, a part of that might be reflected like this. Now observe, I increase the angle further, and I reach this point, Observe this carefully. I reach this point such that, you know, the angle of incidence is such that the refracted ray is now perpendicular. Oh, it is almost meaningless that it is going perpendicular. How can it go parallel to the surface? Basically, nothing comes out. So it has to go somewhere. Out of 100 laddus in the green one, maybe 70 laddus went out, 30 laddus reflected back. In the yellow one, maybe out of 100 laddus, maybe 50 laddus went out, 50 laddus came back. Here, out of 100 laddus, nothing can go out because it will come almost like this. That means hardly anything goes out. So almost everything will come back over here. And if you increase the angle further, oh my God, it can't refract more, guys. It has to be inside 100 laddus, 100 laddus, 100 laddus, 100 laddus. Here in yellow and green, 100 laddus, maybe 50, 60 laddus go out, maybe 40, 50 laddus come back here. So this part is nothing but where your total internal reflection begins. Whereas here there is partial reflection. This is partial reflection. Is that clear, my dear students? What is the concept of total internal reflection? I hope this colorful diagram has helped you a lot. Yes, awesome. So my question to you is, will this only happen from dense to rare, or can it happen from rare to dense also? Imagine this is rare, this is dense. Can it happen for rare to dense? I don't think so. Because when it is from rare to dense, it will always come out. Rare to dense, it will always come out. Rare to dense, it will always come out. Rare to dense, it will always come on the other side. So it is getting refracted for this angle also, for this angle also, for this angle also, for this angle also. So there is no total internal reflection. There is no total internal reflection when light goes from rare to dense. When light goes from rare to dense, it only happens from dense to rare only. Dense to rare only. Very good. So when that TIR happens, if this is refractive index of dense, this is refractive index of rare medium, and just when it begins, the refracted ray has almost become 90 degrees. This angle IC is called as the critical angle. What is it called, my dear warriors? Critical angle. Critical angle. Critical angle. So if by chance my angle of incidence is less than the critical angle, will the light get reflected only or partially reflected and partially refracted? Will it get partially reflected, partially refracted? Come on, answer this in the chat box. Answer this in the chat box. If I is less than IC, what do you think will happen? There will be both refraction and there will be reflection also, partially. Both will happen partially, because if it is less, it will go out. If it is more, I is more than equal to IC, then only reflection happens, nothing comes out. Only reflection happens, nothing comes out. Very good, my dear students. Very good, my dear students. You have answered it absolutely correctly. So, what might be the angle of, what might be the critical angle? How do we find that out? Well, use Snell's law. Sine of IC by sine of, what is the angle of refraction? This is angle of refraction. That is R, which is 90 degree, is going from dense to rare. D mu R. D to R. It's going from D to R. Sine 90 is 1. So sine of the critical angle is D mu R. But very rarely you are given refractive index of the rare medium with respect to the denser medium. Usually things are like refractive index of water with respect to vacuum, refractive index of glass with respect to air, refractive index of diamond with respect to air. It's always generally dense with respect to rare, what you are known, what you are given. So this is little bit not so natural. So I don't like to leave the formula in this nature. So what I do is, I write it as sine of the critical angle is 1 by, remember, reciprocal. 1 mu 2 is reciprocal of 2 mu 1. So mu here R and then D. That's the formula that you are going to remember. Critical angle sine is R mu D, or denser's refractive index reciprocal. That's all. Yes, 1 by whatever is given. Always try to make it big. Meaning, imagine some material is there, mu1, which is having a refractive index of 2. Some other material is there whose refractive index is 3. So from where to where light should go for TIR to occur? From 1 to 2 or 2 to 1? So for TIR, light should go from 1 to 2 or 2 to 1? Light should go from 1 to 2 or 2 to 1. Come on, answer in the chat box. Answer in the chat box. Come on, my dear students. Answer in the chat box. Let's make it 1.5. Looks good then. 1.5. Yes. Where should light go from? Always from dense to rare. Dense to rare. So 1 to 2. This is dense. This is rare. Correcto? Perfecto? Awesome. Then if I ask you, find the critical angle, sine of IC will be 1 by refractive index of the dense with respect to rare. So when you find the refractive index, you have to divide these two. Now tell me one thing, will you divide 1.5 with 2 or will you divide 2 with 1.5? Which one is correct? Which one is correct? Is it this or this? Answer. Let me say who are the smart people over here. Who are the smart people over here? Come on, my dear students. If you do this, then the denominator becomes smaller than 1. 1 by 0.9, 0.8. We'll make it bigger than 1. Sine value can't be more than 1. If you make sine value, imagine something like this, sine value is 1 by 0.8. It's going to be more than 1. Sine can't be more than 1. It's meaningless. Your physics teacher, maths teachers will slap you. One tight slap. How did you write sine value or cos value more than 1? You cannot do that. So don't even think about this. This will be correct. You will put 2 by 1.5. That's all. 2 by 1.5 will be correct. So it will be 1.5 goes on the top and 2 stays below. So 3 by 2 into 2, which is 3 by 4. 3 by 4. Sine IC is 3 by 4. Therefore, IC will be sine inverse 3 by 4. Is that clear? Understood? Oh? Very good. That's how you solve it. Always sine values have to be less than 1. You can say 3 by 4 is less than 1. Perfect. No issues at all. I have no issues. You know, there are many things which are dependent on total internal reflection. And one such thing happens in the desert. One such thing happens in the desert where the air below is hot and the air above is basically cold. Air above is basically cold. And when the air is hotter, it becomes rarer. That means the refractive index is much lower. When it is cold, it is dense, and you will see the refractive index is much higher. Relatively, this is of air. Now, from the sky, which color comes? Sky is blue in color. Everybody knows that. From the sky, which color comes? Blue, because sky is blue in color. Awesome. Very good. So the blue color from the sky is coming like this. Okay, now visualize multiple layers. Visualize multiple layers. Let me just draw. Look at this. Light is going from dense to rare. Dense to rare. So that means it must bend. Oh my God. What is it? Away from the normal. It must bend away from the normal. It is going from dense to rare. It must go again away from the normal like this. And maybe just over here, it might just become the critical angle. What if it just becomes the critical angle because your angle is slowly increasing? Then it will no longer refract, and if it no longer refracts, it will reflect, and then it will go like this and like this. So maybe it will go like this, then like this, and so on and so forth. So there is total internal reflection happening because light is going from dense to rare, and maybe there is an observer here. Let me show the observer in a different way. Okay, maybe there is an observer here. What will he think? He will think, oh my God, the light is coming from here. He will feel some blue shade is over here. Some blue shade is here. That means he will feel as if water is there, but actually it is an image. It is an image of that blue color of the sky which feels like water. That person will run here, but he will get tie fish. Fool. He'll become a fool. He'll be like, oh my God, water was not there. This effect is called as a mirage. What is this called? Mirage. Is that clear, my dear students? Is that clear, my dear students? And you know exactly opposite happens. Exactly opposite happens. If bottom is cold, opposite, right? So this is cold, so mu is higher, and this is hot. This is hot. Then you know what happens? The light from here might get totally internally reflected, and it will go like this. So imagine there is a person standing here, and maybe, just maybe, there is a ship or a boat or something over here. There is a ship or a boat or something over here. What that person will feel is that it is coming from here. he will feel that the ship is flying in the sky. He will run like a mad fellow. And this used to happen many centuries back when they did not understand this phenomena. So enemies used to attack when this effect used to happen, and these people used to think that, oh my god, their enemies are coming in flying ships. What am I seeing? That time aeroplanes were not there. They used to get scared, they used to run for their lives, and then the enemies used to attack. So this effect, by the way, is called as looming. It's exactly opposite. It's exactly opposite of your mirage. Exactly. This also happens in summer. Correct. There are many more examples of total internal reflection, like for example your diamond, which is cut into some nice cuttings, and because the refractive index of diamond is very high, that means the critical angle sin IC, which is 1 by mu, that critical angle is very low. That means there is total internal reflection which happens very easily, because the critical angle is only very low. So once the light ray enters in, you will see that most of it is just going to be reflected multiple times like this, okay, and before it comes out. So the observer, because of those multiple reflections, you will see the shining of the diamond. The shining of the diamond is because of this. Not just that, even you use optical fiber or optical cables, optical fibers or optical cables, where you send signals in the form of light. So the light enters in, and once it enters in, it only gets internally reflected. Nothing comes out unless it reaches the other side. So your signal is sent in the form of light, which gets totally internally reflected. So this is basically your optical fiber cables, your internet cables. These are your optical fiber or optical fiber. Okay, I think it is ER. Yeah, optical fiber. Correct. Cool. Understood? Aren't these examples really fascinating? Be it looming, be it mirages, or be it optical fiber, or even the shining of a diamond. All these are some amazing examples of total internal reflection. All right. So how about we start with the next part, which is apparent shift and all of that. Let's start with that. Okay. Ready for it? Let's go, my dear warriors. Everyone? Awesome. Then we'll do some questions also, don't worry. So, has it happened that sometimes this is your swimming pool, there is water filled over here, and there is a pandu standing, and you might have seen that the swimming pool appears to be little bit shallow when water is filled, but when it is empty, then it feels, oh my god, it was so deep. I thought it was only this much. What is the reason for that? If you look at the rays of light which enters Pandu's eyes, you are going from rare to dense way, so you should bend up towards, it will be something like this. You can show more rays of light. Which come like this. Okay, sorry. From here, maybe you can show one more over here. Yeah. This is how the rays of light come. This is your object. The rays of light are coming like this. If you extend the rays behind, like this, you will feel as if it is coming from a place here. You will feel that the image is somewhere here. That means you will feel that it is a shallow pond. It feels as if the rays are coming from this side. Yep. Haven't you felt that? So this is the concept of, apparent depth, or basically height, where you perceive only in a very different manner. Actually it is not there. Actually it is somewhere else. So it is apparent. Apparent means something what you feel, something what you see, what is apparent to you. But it is, actually something else. Actually it is more deep or less deep or whatever. So there are two scenarios in this. Let me show them to you. The bottom one is dense, the upper one is a rare medium. First time, the object is here, this is your actual height or actual depth. Second time, the object is over here, so this is your actual height, What happens is, in this particular case, when the object is in the dense medium and the observer is in the rare medium, if you show the ray diagram, it will be very, very clear. Like the rays which come from the dense to the rare, they will go away from the normal. All the rays that you show, they will definitely, go away from the normal. And if you extend them backwards, then you will see that they are coming or appear to come from this particular point, which is basically your image. This is your apparent depth. It feels as if it is coming from here. These rays are going like this. It feels as if they are coming from here. That's the apparent depth. So the observer is right over here. In this case, if you draw the ray diagram, it will look something like this. You are going from rare to dense, so it should bend towards the normal, something like this. And when you extend them backwards, you will see that they meet somewhere over here. This is where your image is, and this becomes your apparent height. So there is a very funny example of, the birds which hunt fish. I'm pretty sure you would have heard or seen many birds which hunt fish by diving into the water. Maybe the cranes and so many other birds which are migratory birds and all of that. The fish wants to come on the top because it wants to get more oxygen. The bird wants to dive down and catch that fish when that opportunity comes. But the fish is not a fool. It knows from its ancestors that, birds are going to come and eat me, so it spends very minimal time, as much as needed. But in that time only the bird also makes its move, and the fish has to be very careful. So observe this carefully. If this is a fish eye, bird's viewpoint, and there is a fish here, the bird will feel, oh my God, the fish is not here, it is here. It will feel that the fish is much closer to the surface of the water, correct? So when it dives, it will think that, oh my God, I don't have to dive so much, it's very close to the surface. But when it tries to catch, it will be like, oh my God, what is this? I am looking like a fool now. What a foolish bird. Let me hide my face, let me run away. It will run away because it will realize, oh my God, the actual fish was much deeper. Yes or no, my dear students? And the exact opposite over here. From the viewpoint of your fish, understand what is happening. It feels that the bird is here, but actually it feels that the bird is here, but actually the bird is here. It might feel it is far, but it is actually closer. So by chance, if the fish is chilling, oh, the bird is very far away, chill, I will nicely swim aram se, I will swim aram se. Suddenly that bird comes and catches it, will be like, oh my god, what nonsense. I thought the bird was far away. So that's why all the fishes must attend Shreyas Sir's class, ray optics, especially this part. And even the birds should also attend this class so that they know how to catch the fish. Yes or no? So let's call all the birds and fishes. Please. Why there are no birds and fishes? Very good. So what's the formula then? What's the formula then? This is smaller, this is more, right? So apparent depth is actual depth divided by mu. Mu is more than 1 in this case, in this particular case, in the left one. Whereas in this case, you can see the apparent is more. So apparent is the actual multiplied by mu. So that's the only difference, divide or multiply. That's all. Divide or multiply. That's it. Who is that bird? Sharat, thank you for getting the crane. Yes, thank you for getting the fishes. See, so loyal and so sincere students. Teacher told to get fish and bird. Only few students are getting fishes and birds. Come on. Where are all the sincere front bencher students? Back bencher students are, I think they are eating the fish. Sir, I ate the fish, sir. Very nice fish curry I ate. And another person is, sir, I ate the chicken, sir. Very nice, tasty bird, sir. Yum. Sir, my goldfish and clownfish are listening. Very good, Janice. I hope they don't get ever hunted. Okay. Now observe if by chance this is some medium, refractive index mu. There is an observer here. This thickness is, let's say, T. If I mark an object over here, because it's in the dense medium and I am in the rare medium, it will come closer. It will come closer. Yes or no? Vishnu, thank you for getting those birds and fishes. Thank you so much. Thank you, Dina. Thank you, Krishna. Thank you. We have a fish market and a bird market. है ना? Common dialogue by so many teachers. Is this a fish market? Why are you guys making so much noise? I don't know. Do they really make so much noise in the fish market? They make a lot of noise in random vegetable market only. Why do you have to go to fish market? Fish market is always smelling. You don't open your mouth, your nose only. You'll be breathing through your mouth. है ना? So I don't think I'll be talking in a fish market. In a fish market, I'll be closing my nose and just breathing through my mouth. In vegetable market, I will be talking. So I am the teacher who tells the students, is this a vegetable market, not a fish market? Yes. So now what we have over here is, this is an object. This is an object. Over here, this will appear to be closer, somewhere here. Okay. So it is T inside, T depth inside. So this is your actual depth. But the image will come right over here. So this is basically your apparent depth. H apparent will be H actual divided by mu. H actual is thickness divided by mu. Cool. But I don't want that. I want to know by how much did it shift. That is that delta. So how much is that shift? That shift delta, how much it is? Come on, my dear students. That shift delta, how much it is? Actual minus the apparent. H actual minus the apparent. Actual is T. Apparent is T by mu. So won't it be T into 1 minus 1 by mu? Oh, that is my delta. That is my delta. That means this point has come over here. That is the shift. What that also means is one more thing. You know what? You know what? Everything behind this, everything and anything behind this will also shift like this. Anything over here also will shift like this. Anything over here also will shift like this. Anything over here will also shift like this, all by delta, 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 delta. The entire world behind shifts by delta, because it's like the back part has come ahead, so the entire world has come ahead by delta. So that's the reason why when you look through a glass slab, it feels things have come closer. You try using a glass slab on a piece of paper, it feels like the alphabets or the pages of the book have come on the top. That's the reason for that. This is that apparent shift. This is that apparent shift which happens. Okay. So again, a very important formula. Very, very important formula. The entire world behind the glass slab shifts. Is that okay? Is that okay, my dear warriors? Perfecto. Can we move ahead? Okay, so what if I have a container full of multiple liquids? 1, 2, 3. Observer is over here. Question is, how much does this shift by? How much does this shift by? That's the question. What will you do? Treat it like multiple slabs. So when you have multiple slabs or multiple layers of the liquid, then the total shift delta will be shift 1 plus shift 2 plus shift 3 and so on and so forth. So it will be thickness 1 into 1 minus 1 by mu 1 plus thickness 2 into 1 minus 1 by mu 2 and so on and so forth. That's all you will do. Just add each of the shifts. Isn't that right? Zia, I don't think so. We'll be ending it at apparent shift. Now we are going to just go to the problems part. Okay, see, here is the first question. We are just going to do these problems and we'll be continuing with ray optics in part 2. Okay, in the next week. Is that fine? Okay, cool. Chalo, let's do this. Come on, my dear warriors. The image of this point P, where will it be when viewed from the top? So I think there are multiple layers over here. This is some 1.5, this is 1.5. This is air over here. That means it is 1. So the total shift will be thickness, which is 1.5 into 1 minus 1 by mu, which is 1.5. Again the same thing over here, 1.5 into 1 minus 1 by 1.5. So 1.5, what is 1 minus 1.5? 1.5 is 3 by 2. So 2 goes on the top. Again the same thing repeated, so into 2. 1.5 is also 3 by 2. 1 minus 2 by 3 is 1 by 3. This is 2 times. 2 cancels, 3 cancels. So 1 centimeter is the shift upwards. It always comes closer to the eye. So it shifts 1 centimeter above that point. Hence it is the D option. How many of you got it? Very good. Keep it up. And here comes the next question up on your screen. What does it say? Consider the situation. There is a point O and it is inside a liquid filled till 10 centimeters. Refractive index of the liquid is given. From the surface till the mirror, oh my god, there is a mirror also. The distance is 5 centimeter. Question is, what is the distance of the image from the mirror after reflection from it of an object at the bottom? Distance of the image from the mirror after reflection. Okay, observe first what will happen. The rays after they come over here, dense to rare, so it will bend like that, and then it will reflect, like this. This is how the rays will go. So for the mirror, I don't think the object will be seen here. For the mirror, the object won't be seen here. The object will be seen somewhere over here. What do you think is that particular depth? What do you think is this particular depth? Do I know this? H apparent? Yes, definitely. H apparent is the actual depth divided by mu. Actual depth 10, refractive index 4 by 3. 10 and 4 becomes 5 by 2. So 5 into 3 by 2, 15 by 2, which is 7.5 centimeters. So this is 7.5 centimeters. That means from the mirror, from here till here, this is 7.5, this is 5. So it will be 7.5 plus 5, which is 12.5 centimeters. That's where, if this is the point where the image is formed, that image will now act like the object for the mirror. Correct? So if this is the object for the mirror, where will the image be? Exactly same distance behind. Where? 12.5 centimeters behind the mirror. So option B must be correct. Check this out. Yes, very good. Proud of all of you. No, D is not the answer. Doctor is not the answer. Delhi is not the answer. Yes, be little careful. B for biology. B for biology is your answer. Cool. Let's go ahead. Next question. One face of the slab is 6 centimeter thick. Object is 8 centimeters in front of the first face. Forms an image 12 centimeters behind it. Refractive index of the glass is how much? That's the question. Let's draw the diagram. Without it, it's not going to be easy. One face of the slab is 6 centimeter thick and silvered. So this is a slab. Okay, it is 6 centimeters. It is 6 centimeters thick and it is silvered. Where? Here. Okay. An object is held 8 centimeters in front of the first face. 8 centimeters in front of the first face. So this is where your object is. Okay. It forms an image 12 centimeters behind the silvered face. 12 centimeters behind the silvered face. So this is where the image is formed. Question is, what is the refractive index? You know what I will do? I will simplify the problem in a very different way. And when I say I'm going to simplify the problem in a very different way, what I'm going to do is, what does a mirror do at the end of the day? Mirror just replicates whatever is there in the front, it puts it behind. If there is potato in the front, it puts a potato behind. If there are 2 tomatoes, it puts 2 tomatoes behind. If there is a glass slab in the front, it makes another glass slab behind. So the equivalent diagram must look something like this. This is the object. It makes another glass slab. So it becomes like one huge glass slab of width 12 centimeters. Correct? That's what it becomes like. Correct? And it's as if, now the image is right over here. So it's like seeing the object. Through a glass slab. It's like seeing an object through a glass slab. Just think about it. If I try to see an object through a big glass slab, how much closer will it get? That's all you need to think. It's like seeing an object through the glass slab. The shift will be thickness into 1 minus 1 by mu. Thickness is 12. 1 minus 1 by mu. Oh, I need to know how much is it shifting by. Think about it. So remember, what does a mirror do? Whatever is there behind, it puts it in the front. Whatever is there in the front, puts it behind. So if the image was here, which was behind, if I replicate it on the other side, so I1 will be over here. If something is in the front, it puts it behind. If something is behind, it puts it in the front. If you don't like this, no issues. We can do one more thing. Like I said, what does a mirror do? Whatever is there in the front, it puts it behind. So do one thing, shift the object behind. So you will see the object will be somewhere here. The object will be basically somewhere here. You open it up. So now you forget this. Now you forget this. You just open it up. The mirror just replicates whatever is there in the front behind. How far was the object from this part of the mirror? How far was this object from this part of the mirror? It was 8 plus 6, 14 centimeters. That means this much will be also 14. This much will also be 14. And this much we already know is 12. This much is already 12. So do you see the shift happening over here? This is basically your shift. This is basically your shift, which is 2 centimeter. The object has come closer by 2 centimeters if you try to see it from here also. It's one and the same thing. You see from that side or see it from this side. How many of you understood this? Clear? So that's it. So the shift is 2. So use the shift formula, thickness into 1 minus 1 by mu. 2 is equal to thickness is 12 into 1 minus 1 by mu. So it will become 1 by 6 is equal to 1 minus 1 by mu. So 1 by mu is 1 minus 1 by 6, which is 5 by 6. So mu will be 6 by 5, which is 1.2. Third option will be correct. Yes. 6 by 5 is 1 by 2. Correct. Got it? Isn't it amazing? Amazing way to solve it. So this trick, you can use it in many places when there is a mirror. Whatever is there in the front, you replicate it. So object was there in the front, you can put it behind. If something was there behind, you can put it in the front also. It's one and the same thing. Cool. Which of the following is not due to total internal reflection of light? Brilliance of the diamond? 100% it is. Mirage? Yes, it is. Working of optical fiber? Yes, it is. Difference between real and apparent depth in a pond is not because of total internal reflection 100%. It is just because of refraction. It's just because of refraction. So I think it should be fourth option. Yes. Which of the following is not, this word is very important, not due to. Not. That word not, if you miss, you will get a wrong answer. Right. If the critical angle is 30, then the refractive index is, direct question this is, if critical angle is 30, what is the refractive index? Mu is 1 by sine of IC. So it is 1 by sine of 30, which is 1 by 2. So 2 goes on the top, it will just become 2, which is option number 1 or Ames. Ames. Yes, that is the correct answer. Very direct question. These kind of questions also do come in the examination. Great. Shall we go ahead to the next one coming up on your screen? Here it is. When a ray of light is refracted from one to other, wavelength will change. What is the critical angle? See, instead of giving you the refractive index directly, they have given the wavelength information. We know refractive index is lambda 1 by lambda 2. So if light goes from 1 to 2, is nothing but lambda 1 by lambda 2. That's it. So all you need to, oh sorry, I put mu 2, lambda 1 by lambda 2. So refractive index will be, what is this? 60000 divided by 40000. So 6 by 4, which is 3 by 2, is the refractive index. So sine of the critical angle, which is 1 by mu. So 1 by 3 by 2, which is 2 by 3. So that is the sine value. So critical angle will be sine inverse of 2 by 3. Sine inverse of 2 by 3, which is option number C. Perfect. 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 We got that. Amazing. Getting the hang of it, my dear students. Critical angle questions as well. Let's go to one more question. This was in 2019. Total internal reflection. When the angle of incidence is equal to the critical angle, then what will be the angle of refraction? Very, very interesting. When the angle of incidence is equal to the critical angle, then what happens? You will see that the angle of refraction is like grazing. This is called as grazing incidence or grazing refraction. That means it is almost like parallel to the surface. Yes, it is going to be 90 degree for sure. Yep, perfect. So IC means it will be 90 degree. Very good, very good, very good. A diver is at a depth, sees the sky in a semicone angle. Why will he see the sky in a semicone angle? If this is the water surface, this is the normal. This is the diverse eye. This is the diverse eye. You will see only certain rays can go out or come in into the ocean at that certain depth. Like for example, I can show maybe this ray which enters into his eye. Maybe I can show another ray which probably enters into his eye. I go even far, then maybe, oops, maybe like this. And then comes a critical point. Wow. And then comes a critical point when it is almost like grazing incidence, almost like grazing incidence. And after that, you will see it's just total internal reflection. It's just total internal reflection. That's all. So you can see only few of the rays from outside can actually enter that person's eye at this depth. Now this is not just here, but it is also here, it is also there, it's also here, it's also there, also here, everywhere. So basically it forms kind of a circle. Basically it forms a kind of a circle, and I hope you can see and visualize a cone over here. Can you visualize a cone over here? Only in this cone those light rays can come in. Apart from that, the light rays will not be able to reach his eye. Is that right? Everyone? Yep. Yes, Sparkle, that's the meaning of Super 6. So Super 6 is basically, we started with the aim of 6 classes per week. So I don't know how many of you realized it's now become more than 6 classes per week. So now the 6 now does not stand for the number of sessions, it stands for the days. Like we'll be here daily throughout the week. Weekends is time for mock tests, assignments or DPPs and quizzes and all those things. So almost 6 days you will see us coming over here. That is what Super 6 stands for. So that it's there in your mind. It's not about, giving you 1 year plan or 2 year plan. Yes, we give that. But at the same time, this Super 6 stands for we are here every day. You'll see either some session or some tricks which we are giving. Something is always there on the channel. Something which is going to be helpful for you on, for your NEET examination. That's what we stand for over here. That's why you should subscribe, and that's why you should smash the like button. Yep. So if this is a cone, do you see this is a semicone angle? This is the semicone angle. Semi means half. Semi means half. So this is basically your semicone angle. This is your semicone angle. Either this one or this one. One and the same thing. But I'll tell you what. You just drop a perpendicular over here on the surface. You will immediately realize this angle over here is the critical angle because this is 90 degree and these two lines are parallel. These two are alternate angles. These two are alternate angles. That means the semicone angle, this semicone angle technically is the critical angle, which is 1 by mu, or is basically IC, which is basically sine inverse of 1 by mu. You can say that. So basically sine of critical angle is 1 by mu. So it is 1 by 4 by 3. That means it is 3 by 4. So critical angle is sine inverse of 3 by 4. Correct. Sine inverse of 3 by 4. Where is it? Option C. Captain Shreyas is the answer. Very good. Awesome. Did you understand this question? This question is very, very high weightage type of question. It has been repeated in many ways. Sometimes they ask you the radius, sometimes they ask you the area, sometimes they ask you the angle. If they ask you the radius, you can use trigonometry over here. If you notice, this becomes the radius. This becomes the radius. From here till here, this thing becomes the radius. You can see this is the radius, this is the angle, this is the height. This height is already known. So you can find the radius also if you want to. Cool. Okay. Very good. Awesome. So I think we will end the class right now over here. There are many slides like you can see. So we will take it up in the second part. We'll take it up in the second part. For now, can you just comment after the session ends? Optics seesaw 1. Optics seesaw 1, because you just saw optics, the first part. So comment it, and yes, do not forget to smash the like button. Please do that. There is a DPP which is there in the description box. Please check that out. Solve the DPP. It's free of cost. You just have to enter your login details. In case you do not have a free account, create that free account in Vedantu. Next thing is weekly mock test happening on Sunday, free of cost from our side. So make sure you give that as well. And also keep that in mind that you are going to get the PDFs, everything, after the entire session is over. So for now, I'm not going to send the PDF. After the second class, I'll send you the PDF of this, okay, at once. Cool. So thank you very much. Have a great night. See you very soon. Bye bye. Hasta la vista, Captain Shreyas signing off.